Welcome everybody to our second day of ACM WiSec 2020. Today we have more of an exciting program with different sessions. Please remember that today there is no keynote, but the session 5 will be split into 3 different sessions for demos and posters. So this is the one exception. This is the one session starting here local time at 16:10 Central European Summertime that will not be live streamed on YouTube. And instead of one video conferencing meeting, there will be 3 meetings in parallel. The main video conference meeting will stay open, but there will be no activity in there. So please choose which of the demo and poster sessions you would like to attend. You feel free to jump between them and find the correct video meeting, the correct Zoom link in the program overview on the Mattermost channel for the program overview. That also brings me to Mattermost as our virtual conference venue. Please use it as a way of interacting. We have that self-introductions channel with a great number of self-introductions already in there. Please take some time, take a few minutes to just read through, browse through, identify people who have similar research interests to your own, and feel free to just contact them. Either direct messages on that Mattermost system or maybe even direct email. Feel free to use that as interaction, or the other channels like our coffee break channel that we have to get to know each other a little bit better.
Yeah, and part of that interaction, don't forget to vote. We have an ongoing vote for the best teaser at WiSec 2020, and within the next hour or so, there will also be another voting for the best poster and demo awards.
So please keep your eyes peeled on announcements in the channel of how to vote there. You should already, all of you should already see the one channel for the best teaser voting that is already ongoing. With that, we hope that you will also enjoy the second day, and we hand over to start the first session.
Good morning or afternoon, everyone. I'm Brad Reeves. I'm going to be your session chair for our first session this morning, session 4, which covers security across the wireless stack, and specifically security analysis from the physical layer all the way to the application layer. We've got 4 great talks for you this morning or afternoon or evening or whatever it is, wherever you are. And we're going to kick it off with a talk about malicious libraries that end up in Android apps. And so our first speaker, Zicheng Zhang, is going to talk to us about their paper called An Empirical Study of Potentially Malicious Third-Party Libraries in Android Apps. So Lucas, take it away.
Mr. Chairman, ladies and gentlemen, it is an honor for me to have the opportunity to speak at this meeting. Our work is an empirical study of the potentially malicious third-party libraries in Android apps. Android system has already become the most popular mobile system around the world. The rapid development of Android apps benefited from the third-party libraries that provide well-encapsulated functionalities. However, potentially malicious libraries, which are PMLs, may bring some security problems. Previous related work provides solid ground for understanding the security problems of these libraries. However, most of them focused on the advertising libraries or just individual case studies. We still need a comprehensive study on the behaviors and the features of PMLs in the wild. So in this paper, we carried out the first empirical study on PMLs based on a large-scale APK dataset, which includes 2 stages. In the first stage, we designed an automated tool to extract and identify enough PMLs for analysis. And the second stage is to conduct a comprehensive analysis for the PMLs. And we focus on the following 4 aspects: library, repackaging, expose potentially malicious behaviors, permissions, and the developer connections with their corresponding apps. To capture enough PMLs in the wild for our study, we need an automated tool for PML extraction and identification. After reviewing the previous research, we did not consider the tools based on a predefined database or whitelist because they cannot identify unknown libraries. We choose to use the approach which directly extracts libraries from apps by clustering and filtration. A tool called LabD could meet some of our requirements, but its low speed and incomplete dependency significantly affect our analysis efficiency. So we designed LabExtractor. It can quickly and accurately extract libraries from large-scale apps and perform PML identification. Here is the overall design of a LabExtractor. It is divided into 5 steps. Firstly, we extract the dependencies from the APK file, get the file dependency and structures, and construct the library candidates. Then we generate the feature value for each candidate and obtain the third-party libraries by grouping and filtering according to their feature values. Finally, we combine the reports of various total and a behavior matching to identify PMLs. The first step is to extract dependencies from the apps. First, we decompile the input APK file to get the smart code and parse the following 6 kinds of dependencies between classes and the file structure from the code. The 6 dependency files cover all possible dependencies between 2 classes, which can make the extracted library as complete as possible. The second step is to construct the library candidate. First, we build an inclusion dependency graph, which is an undirected graph. Each of its nodes is a package in the file structure, and if 2 packages contain files that have dependencies, there will be an edge between them. Then we eliminate 3 kinds of redundant packages, including packages of Android SDK and application's own code, as well as some empty app packages that do not contain files, because they will connect the different libraries together on the graph or output empty packages, which will reduce our efficiency. Then we divide the weakly connected components on the inclusion dependency graph. Since there is no dependency between the 2 different components, which means each of them have independent functions, each component is regarded as a library candidate. The third step is to generate feature value for each library candidate. First, we design a special algorithm to generate the class feature values, including 4 rounds of calculation. In the first round, for each class, we got the relative path from that class to each of its dependent classes and replace the names of the packages and classes with the letter A. We call this special path the corresponding string of each dependent class. If the dependent class is a native Java class, we will directly use the class name as its corresponding string. Then we sort the corresponding strings of the various dependent classes and concatenate them to get the dependency file string. Finally, the 6 dependency file strings are concatenated into a single class string and hashed to get the class feature value in this round. And in each subsequent round, we will change the corresponding string of the dependent class to the feature value of that class calculated in the previous round and repeat the same steps. After that, we use the class feature values generated in the 4th round to obtain the package feature value by sorting and concatenating and hashing, and the same operation is repeated to obtain the candidate feature value. This process is fast because the dependencies are easy to acquire. And as we use the special relative path, the package name obfuscation will not affect the result. The fourth step is candidate clustering. We group the candidate libraries according to their feature values. When the number of candidates in a group reaches a threshold, this group of candidates is regarded as a real third-party library. The reason for this is that there are some packages that are not libraries while constructing the candidates, but because these packages only exist in a few applications, they will be eliminated during this process. The threshold is set by using a whitelist of common libraries given by a previous work. We compare the filtration results on the different thresholds with the whitelist to find the threshold when the number of unreported is the lowest. In addition, some of the obfuscated package names can be recovered by selecting the most appropriate name in the group after the candidates have been filtered out. The fifth step is PML identification. First, we list 8 types with 23 subtypes of potentially harmful behaviors that may exist in PMLs, which is based on the detection rules of some malicious code detection tools. Our PML analysis is based on these behaviors. Then we upload each of the libraries to VirusTotal for online scanning and perform an API matching based on the behavior list. If 2 or more engines reported as malware and it contains at least 1 potentially harmful behavior, then we record this library as a PML. And here is the dataset. We obtained more than 200,000 apps from third-party markets and 300,000 malware apps with the help of Android Zoo project. Applications from third-party markets will be used for evaluation of the tool and for behavior comparison. Since the libraries extracted from these apps are not always benign, we call them possibly benign libraries, which are PBLs, and malware applications are used to obtain PMLs for analysis. Based on the matching results of the whitelist, we finally determined the threshold 10 and extracted nearly 20,000 libraries from the apps of the third-party markets and obtained nearly 5,000 PMLs from malware apps. In addition, we perform a simple evaluation of the tool, including speed, accuracy, and the ability to handle the obfuscation. Using this tool and LabD to process about 200,000 benign applications, we found that on average, LabD takes more than a minute to process an app, while Lab Extractor only needs about 1 second. And we randomly selected 1,000 apps to run the 2 tools and manually check the correctness of the extracted libraries. The accuracy rate of our tool was higher than LabD. And we found more than 4,000 PBLs with obfuscated package names and further recovered more than 1,000 of them. And it indicates that Lab Extractor is resilient to package name obfuscation. To compare the difference of potentially harmful behaviors between PMLs and PBLs, we also performed behavior matching on the PBLs, and the result is shown in this figure. It shows the percentage of libraries containing a specific subtype of behaviors. Obviously, for nearly every subtype of behaviors, the ratio of PMLs is significantly higher than that of PBLs. Furthermore, we summarize the main behavior characteristics of PMLs, such as obtaining location information, reading device IDs, modifying network settings, and reading the package list. The second stage is to conduct a comprehensive analysis for the PMLs, and we try to answer the following research questions. How many PMLs are repackaged from benign libraries? Does there exist any exposed potentially harmful behavior in PMLs? Which permissions are frequently used in PMLs? What about the connections between the PMLs and their authors? The first part is the library repackaging. If a PML is created by modifying a benign library, its impact may be severe, especially when the victim library belongs to a popular SDK. To identify those repackaged libraries in our PML set, we cluster the PMLs and the PBLs sharing the same packages list into a group and eliminated the obfuscated labs that are not recovered by lab extractor. In each group, we counted the number of potentially harmful behaviors of each library, and once a PBL without such behavior was found in a group, then all PMLs in this group will be considered as a repackaged library of this PBL. In the result, we identified 218 repackaged libraries in 35 groups, which accounts for 4.4% of all the PMLs. To measure the impact of these repackaged libraries, we multiplied the number of its potentially harmful behaviors by the number of associated malware apps, and then used the product to evaluate the impact of these repackaged libraries. The top 10 repackaged libraries with the most significant impact are listed in this table. We found that up to 7 PMLs repackaged net.umi.android, which means a benign library may be used to generate multiple repackaged PMLs. The second part is about exposed behaviors. An Android application can set the parameters of a component in the manifest file so that other apps can access that component. Such a component is called an exposed component, and the exposed behaviors are the potentially malicious behaviors that could be accessed by the exposed components through the call path. This makes it possible for adversary to invoke malicious code through exposed components. To find the exposed components of PMLs, first we obtained exposed components from the manifest files of the PML's corresponding apps, and then matched with the component of PMLs. To find the exposed behaviors of PMLs, we built a call graph for each PML and perform backward path search from the node containing potentially harmful behaviors. And if there is a path to the exposed component, this behavior is regarded as an exposed behavior. We found 133 exposed components in 101 PMLs, and further, we found a total of 156 exposed potentially harmful behaviors in 40 PMLs. The distribution of these behaviors is shown in the figure, among which the most behaviors were modifying network settings, obtaining device information, and reading installed package list. We also found a broadcast receiver, which can monitor the change of the app or device and trigger potentially harmful behaviors. The third part is about the permissions. We got a sensitive permission list given by the Android developer document. Then we obtained the permissions declared by malware apps from their manifest files. Further, we studied the sensitive permissions used by PMLs based on the API permission pumping list. We obtained the permission usage of more than 200,000 malware applications and more than 2,000 PMLs. For both of them, only the top 4 permissions are over 60%. The highest one is about reading device information, while writing external storage has the biggest difference. And the other 2 permissions are about locations. The results indicate that the permissions declared by apps are likely to be used by their corresponding PMLs. The fourth part is about the developer connections. It is quite challenging to identify the developers of PMLs directly, so we explore the connections based on the app certificates, which are assigned by the developer's private keys. In particular, we obtain the certificate from the malware apps and then construct a bipartite graph between the PMLs and the certificates. During this process, we deleted some meaningless certificates and merged the certificates with the SAM developer information. In addition, we also explore the PMLs that associate with only one certificate. In the results, we obtained a bipartite graph between more than 17,000 certificates and more than 4,000 PMLs, of which more than 1,000 PMLs were associated with only one certificate. We found some interesting cases, such as a certificate signed by Baidu Soso, existing in 331 apps. This name does not belong to Baidu, which means it may be used to mislead the developers and users. The certificate having the most corresponding PMLs is signed by APK IDE, which has 370 corresponding PMLs. It is an APK modification tool, and these PMLs may be injected into these APKs using this tool. And for all the PMLs associated with the one certificate, this is the one with the most associated apps, 4,060 apps. Its certificate is signed by the ACM, which is also associated with other three PMLs. Since these libraries are only associated with ACM, they may share the same author. In summary, we make the following assessment. The main behavior characteristics of PMLs contains obtaining location information, reading device IDs, modifying network settings, and reading the package list. A benign library may be used to generate multiple repackaged PMLs. Exposed components are not common in PMLs, but there are still some unsafe examples. The main permissions that used by PMLs are similar to their associated apps. Some PMLs may be created by the same author. That's all. Thanks for listening. Is there any question?
Thank you, Zicheng, for that interesting talk. And so if you have any questions for Zicheng or any of our authors this session, make sure to log in to the Mattermost channel that we have for the session 4 Q&A. Post your questions there, and at the conclusion of all of the talks in this session, we'll have one large Q&A session for all of our authors. So next up, we have Dennis Heinze, who is going to talk to us about his work along with his colleagues on MagicPairing, how Apple actually pairs its Bluetooth devices together, and he's going to talk about the security of that. So please take it away, Dennis.
Hi, I'm going to talk about MagicPairing, which is Apple's take on securing Bluetooth peripherals. In our work, we analyzed both the design and the implementations of this protocol. So let's look at what MagicPairing actually is. Imagine a user that owns multiple Apple devices and just bought the AirPods, which are Apple's Bluetooth headphones. Usually in Bluetooth, the user would have to connect each of these devices individually to the AirPods, which would take a long time. So one of the solutions that Apple came up with is a protocol that can be used for seamless pairing across these devices. And the idea is that you explicitly pair one of these devices, and then automatically all the other devices are also paired with the AirPods. And this is all done using iCloud. This protocol is called MagicPairing, and it's actually quite interesting. So firstly, Bluetooth pairing had many issues in the past, and the question is, can MagicPairing maybe solve this issue of Bluetooth pairing? And secondly, it's a proprietary extension to Bluetooth pairing. Does it add attack surface, and are the implementations actually secure? So this is what we basically looked at. And one of the first things we found is that Apple actually maintains 3 completely different Bluetooth stacks. So one for macOS, which is their desktop operating system, then another Bluetooth stack for iOS and all its derivatives like tvOS and iPadOS, and then RTKitOS, which is the real-time operating system that runs on the AirPod. What we did there was static analysis. So we reverse engineered the iOS Bluetooth daemon, the macOS Bluetooth daemon, and even the AirPods firmware. Something else that is very interesting for this kind of research is Apple's packet logger. So essentially it's comparable to Wireshark. It can be used to log and inspect Bluetooth traffic, both on macOS and also on iOS when the iOS device is connected to a Mac. The advantage over Wireshark is that Packet Logger even contains the capability to dissect some of Apple's proprietary protocols, which was a huge help here. So yeah, what you can do is reverse engineer Packet Logger itself and look at the protocol parsing code to understand it a bit more, and also you can do dynamic analysis and analyze the traffic that you can observe between the AirPods and any device. So let's get into MagicPairing. Essentially, MagicPairing has two phases. The first phase is the actual key creation and distribution, and the other phase is executed whenever you do the actual pairing between a device and the AirPods. So let's start with the key creation and distribution. It all starts with a master key and master hint that are associated with the user's iCloud account. And these are used to create accessory keys and accessory hints for the MagicPairing devices. So for each pair of AirPods that you own, an accessory key and an accessory hint is created. And this is done by using a Bluetooth address blob, which is basically a mutation of the Bluetooth address of the device. So the master key is used to encrypt this Bluetooth address blob to receive the accessory key, and the master hint is used to encrypt this blob to receive the accessory hint. Now, this key information needs to be transmitted to the AirPods before MagicPairing can be used. So the first time that the AirPods are paired to any device, the classical Bluetooth pairing has to be used. So usually this is secure simple pairing. And once these keys are exchanged, all subsequent pairings can use MagicPairing as a protocol. So let's look at how this pairing process actually works. It starts off with a hint message by the initiating device, and this is usually the iPhone or a Mac or the host device and not the AirPods themselves. And this message contains of the accessory hint, a nonce, that is just a random nonce created on the host device, and a ratchet value. This ratchet value is basically just a counter that is initialized with 1. And when the AirPods receive this message, they execute two key derivation functions. The first key derivation function is for ratcheting the accessory key, and the second key derivation function is to obtain the so-called SIV key. So firstly, the ratcheting is done by synchronizing the just received ratchet value from the host with the local value that is stored on the AirPods. And on each iteration of this ratcheting process, the accessory key is used as a key to encrypt a static string, and the result will then be the new accessory key. Once this ratcheting process is done, the ratcheted accessory key is used to encrypt another static string to finally obtain the SIV key. And in addition to that, the AirPods also create a random value, which we called rand AirPod here. Now they respond using a message called ratcheting message. This basically contains of a payload that is encrypted using the just generated SIV key. And the payload consists of the random value that the AirPods just created, the nonce that was received in the previous hint message, and the Bluetooth address of the AirPods. In addition to that, the AirPods also transmit their own ratchet value. Now the host, for example, the iPhone, can do the same two key derivation function steps. So firstly, the ratcheting process where the accessory key is ratcheted, and then the second key derivation function to obtain the SIV key. In addition to that, the host also creates a random value, which we call rand host here. Now that the host also obtained the SIV key, the just received payload can be decrypted and unpacked, and the host also obtains the random value of the AirPods. Now a second AIS SIV packet is created now by the host. It's similar to what the host just received from the AirPods, but the payload looks a bit different. So again, it contains the nonce, then it contains the random value the host just created, it contains the random value that was just received by the AirPods, and it contains the hint. The AirPods can then decrypt this and check the values. So what they can check, for example, is if this is the nonce that was used in the previous message, if this is the random value that they just created, and if this is still the same hint. If this is true, then at the end what you have of this process is that both of these devices know the random value of the other device. And this is important because these random values are now used to finally derive the Bluetooth link key. And this is done using the key derivation function number 3. First, they create a session pre-key, 2 session pre-keys that are then XORed, and then finally the Bluetooth link key is obtained. And as both devices know about the rand values here, both devices will obtain the same Bluetooth link key. This link key is then sent to the Bluetooth controller, and an encrypted and authenticated connection can now be established. To understand this a bit better, let's just quickly get into how link keys are usually handled in Bluetooth. Usually, if a Bluetooth connection is established, the Bluetooth chip at some point needs the link key to create the encrypted and authenticated connection. However, the problem is that Bluetooth chips usually don't have permanent storage. So this link key needs to be stored somewhere else. And this is usually on the host or on the operating system. So at some point of the connection process, the Bluetooth chip will send a link key request to the operating system. The operating system usually has some sort of lookup table where both the Bluetooth address and the corresponding link key are stored. So what the operating system can then do is from the Bluetooth address obtain the link key from its storage and then send a link key request reply to give the Bluetooth chip the link key. And now the Bluetooth chip can continue creating the authenticated and encrypted connection. What MagicPairing can now do is just step in between of this process. So if an iPhone wants to pair with the AirPods, at some point they want to encrypt their connection, and the Bluetooth chip will send a link key request to the host. Now, instead of doing some kind of lookup, the host will then initiate the MagicPairing process, steps 2 to 5. This now happens in between of the link key request and the link key request reply. So all the data that is exchanged during MagicPairing is not encrypted. Once the MagicPairing process is done, both of the connecting devices should have the same link key, and both of the devices should be able to respond to the Bluetooth chip with the same link key and the link key request reply. And now these two Bluetooth chips can continue creating their encrypted connection. From this, you can see that MagicPairing is actually standard compliant, so it should work with every Bluetooth chip and every Bluetooth stack implementation, which is actually pretty nice. Let's have a quick look in the security properties of MagicPairing. So the ratcheting process provides forward secrecy, which means that if an attacker at some point gets knowledge of an accessory key, they cannot go back in time and decrypt or obtain older Bluetooth link keys. However, it does not offer post-compromise security. So once the attacker has the accessory key, they can observe MagicPairing traffic and also derive link keys for future pairings. However, this is not extremely likely because the accessory key is never transmitted over the air. The accessory keys only reside on the respective devices. Something else that's interesting is that MagicPairing only uses symmetric cryptography, and this is probably because it just requires less computing power than asymmetric cryptography, and this is great for IoT devices, and you could say that the AirPods are a kind of IoT device. Now let's get back into the implementation of MagicPairing. As I've mentioned before, Apple maintains 3 different Bluetooth stacks, which also means that they sort of have to maintain 3 completely different implementations of MagicPairing, which is interesting because now each of these devices offer a different attack surface. And one of the things we immediately recognized when we started to analyze MagicPairing was the code quality. So when we went through the debug strings that you can find in there, and on macOS you can also find symbols, we immediately saw that there are quite a few spelling mistakes or differences in spelling. So of course this is not necessarily a security issue, but it certainly hints at the fact that there wasn't a very long QA process over the MagicPairing code. So for example, you can see here that they spell ratchet in this one way and also in this other way. And here's an example of a spelling mistake. So again, of course, this is not a security issue, but in the end, this is one of the things that drew our attention to MagicPairing. And in the end, we can say that not only the strings show that there's a lack of QA, but also the implementation. So after some manual analysis, we decided to quickly implement a small fuzzing setup. And this is actually quite interesting. So for fuzzing macOS over the air, it's quite simple. You just send your fuzzing data over the air, and you can look at logs, and even you can even run packet logger to see what packets arrive, how they look like, and how the Bluetooth stack reacts, and if it just crashed. Something similar applies to the iPhone. So as of iOS 13, you can also use packet logger on an iPhone. You just have to connect it to a Mac, and the Mac can then show the Bluetooth traffic of the iPhone. So something similar here. You can start transmitting fuzzing data and just see what arrives at the iPhone and if it crashes. Now, the interesting part are the AirPods, because there's not really a way to debug them, and there are not really logs you can obtain from the AirPods. So what we basically did is we put in the AirPods, we started playing music, and then we started transmitting fuzzing data. And if at some point the music would stop and you would hear the disconnection or reconnection sounds in the AirPods, you would know that either the Bluetooth stack has crashed or the whole operating system has crashed. And actually we found one crash on the AirPods, but we don't know anything about it except that it crashes something on these devices because it stops playing music and they disconnect, and then after a few seconds reconnect. Now, the fuzzer re-implemented is not necessarily smart because the MagicPairing message format is quite simple. So there are only really 2 different types of messages. There are key messages and short messages. The short message doesn't really contain any payload except for in the status message 1 byte status, and the ping doesn't contain any payload at all. The key messages are a bit more complex, but in the end they are just key value types, and there are not that much different keys in there. So we basically wrote a generation-based fuzzer that would randomly create valid or invalid MagicPairing messages. We transmitted these messages over the air using internal Blue. So we ported internal Blue to run on iOS devices. And yeah, in the end, we just put together the payloads, connected to one of our fuzzing targets, and just sent over the data. And then observed logs and packet loggers. In the end, this resulted in quite a few bugs. Now, we disclosed a lot of them a while ago, and there is not really a response from Apple. So as you can see in the status field, the most recent iOS version and the previous macOS version have still not fixed these issues. However, they are not particularly severe. So the ones that say crash on here are usually null pointer dereferences or something of that kind. And none of the values are really attacker controlled. So it's nothing that would immediately result in remote code execution. But still, it's quite interesting that they are not fixed at all. This same applies to the spelling mistakes. They are still in the code. Yeah. Interesting are two of these bugs, MP5 and MP6. They are not crashes. They are basically denial of service attacks. MP5 can be used against Macs, and an attacker can basically cause 100% CPU load because it can sort of trap the Mac in a ratcheting loop, and it will just continue ratcheting for a long time. Which also clogs the Bluetooth reception thread, which means other functions that are related to Bluetooth don't work, for example, AirDrop. And we found one attack with a sort of strong attacker model, but you can disassociate AirPods and a host device. So in the end, you can say that MagicPairing is actually designed pretty well. However, the implementations are in need of improvement. All these null pointer dereferences are really just something where the values should be checked and then it shouldn't crash. However, the simplicity of the protocol really narrows the attack surface. So on the reception handlers for these different message types, there are really no heap allocations. The heap is really only used when MagicPairing itself is initialized. Other vendors could really benefit from MagicPairing if Apple would sort of provide an API for the initial key exchange. And then, other vendors could use MagicPairing for pairing their devices to all iCloud connected devices of a user. And something really good is once MagicPairing is set up, so once the key material is exchanged, it is completely independent from the usual Bluetooth pairing mechanism. So any future vulnerabilities in Bluetooth pairing will not affect it. So this was the presentation about MagicPairing. Thanks.
Thanks, Dennis, for that interesting talk. I, for one, really enjoyed learning how my AirPods actually pair to my devices. I was always curious about that. So just a reminder, please, if you have any questions for any of our speakers this session, make sure to ask them in the Mattermost channel. I see we've got a couple already, but please, if you have any more, let us know. Next up, we're going to look at a different wireless ecosystem, specifically the cellular network. And so our next speaker, Dominic, is going to tell us about their paper called BaseSAFE, Baseband Sanitized Fuzzing through Emulation.
Welcome to our talk, BaseSAFE, Baseband Sanitized Fuzzing through Emulation, by me, Dominic Meyer, Lukas Seidel, and Shinju Park from TU Berlin from Security and Telecommunications. We propose BaseSAFE, a fuzzing framework for feedback-based fuzzing of firmware blobs, especially basebands. In our proof of concept fuzzing harness, we fuzzed the MediaTek baseband. Why do we focus on basebands in the first place? Well, a baseband is a full-blown operating system running in each smartphone in a coprocessor. So it's running on millions of devices. And the basebands are all written in memory unsafe languages such as C and C++. And their codebase is usually proprietary, complex, and the parsers that are parsing insane amounts of data are obscure and hard to test. what we deem necessary is more automation, so we try to automate. If you look around the software landscape, what tools help automation in finding memory corruptions and low-level bugs? You quickly stumble over fuzzers. AFL, for example. They are known to be very efficient in unearthing memory corruptions by randomly executing the binary and by gathering feedback about the binary that can then be used to generate new test cases. So why has this not been done for basebands yet? Well, it just turns out that fuzzing basebands with coverage is rather hard, as the basebands are hard to reach, obscure, run in their own coprocessors, and so forth. And to our knowledge, nobody publicly has done this in a commercial environment. If it is done at all, the fuzzing happens over the air and no feedback is gathered from it. Fuzzing over the air, of course, has other downsides. It is slower. You have to wait for the phone. You can't see if the phone crashed or if the input already triggered a bug. You cannot reset the baseband to a previous state. And you can add minimal instrumentation to the running binary. Sometimes you already need an exploit to run your own code, depending on the brand of baseband and if it checks integrity before booting. So we thought, well, maybe it's not the right approach to fuzz over the air, but instead take the whole firmware, if we can extract it from the device, drop it in an emulator and fuzz it inside the emulator, where we have faster processing power and a lot more access to the state that the firmware runs in. So for BaseSAFE, we use Unicorn AFL, which is a fork of Unicorn, which is a fork of QEMU, that allows us to emulate different architectures, including, in this case, ARM, or in newer MediaTek basebands MIPS. So what Unicorn brings to QEMU is an accessible API to read and write memory and to hook addresses. So what Unicorn does, it goes through the next basic block that's going to be executed. It lifts it to its intermediate representation and then compiles it down again. And in this step, Unicorn AFL inserts instrumentation, and Unicorn itself can insert hooks. This added instrumentation then can be used by AFL++ as feedback, and we get feedback fuzzing for the emulated target. So we went ahead, took what was there already by Unicorn and added Rust bindings and added a proper architecture that can be used by people writing fuzzing harnesses. And then we were able to also adapt this for our proof of concept fuzzer, which would fuzz MediaTek basebands. The overview over the BaseSAFE architecture, as can be seen in this image, is that we have AFL++, which, as it usually does, collects and mutates seeds and collects the feedback and feeds it into our BaseSAFE process. The BaseSAFE process uses a fork server model, so it runs until it's set up, and then for each new child it forks. But what we also added on top of the old Unicorn AFL implementation is that we can also use a persistent loop. Instead of exiting the program and restarting it from the beginning using a fork, like from the snapshot, instead you just stay in the same execution, you loop back from the top, you call the same function again, which means that by the end of the function you have to first clean up whatever has been altered during the fuzz process. Using this persistent loop over the classic fork implementation of Unicorn increases the speed even more. But also we added a lot of engineering details so that even the normal fork mode is quicker in BaseSAFE than it was in Unicorn before. Of course, MediaTek fuzzing, as we did in the BaseSAFE paper, is just one possible implementation. But for each new target, you will have to write a bit of own code. You'll have to decompile, or never decompile, of course. You will have to find interesting places to fuzz. But then you can use the BaseSAFE API, which makes it very convenient to add sanitization and fuzzing points. The BaseSAFE API consists of mainly the AFL fuzz function. The AFL fuzz function kicks off the AFL fork server, or BaseSAFE fork server in that sense, and communicates back to AFL that fuzzing should be started. The BaseSAFE AFL fuzz function offers a input placement callback, a crash validation callback, and also a counter for persistent iterations. The input placement callback is called for each time AFL tries to execute this target. And what the callback has to do is go to Unicorn and put the memory into the right spot inside the target. The crash validation callback can be called at the end. Like, default behavior is if Unicorn itself errors out with an out of bounds read and out of bounds write, then it would assume it has been it was a crash in the emulator. However, you can override the crash validation callback and then add your own sanitization steps or own assertions, which we do with the heap sanitizer that we will discuss later. Another option you have to set is the exits. So official upstream Unicorn only supports one single exit. We support multiple exits in case there are multiple exits out of a function where we know we don't have to emulate any further. We can stop fuzzing here. And then the persistent iterations. One means that we don't use persistent fuzzing. We just iterate once. And then we fork new, or if there's a multiple iteration set, then persistent mode will loop. So like a 10,000 would loop 10,000 times and then fork again. Sometimes it's good for the target to reset the state completely. For example, if some memory fills up. The bindings itself were written in Rust. About the bindings and about the heap sanitization, my colleague Lukas Seidel will talk a bit now. Lukas?
Yeah, thank you, Dominic. So, as he just mentioned, we improved upon the Rust interface to not only Unicorn, but Unicorn AFL. So we have possibilities to modify emulation state as you would expect from any Rust bindings. You have this access to the AFL++ API Dominic just showed you, and you have also some utility functionalities I will come to in a second. Overall, these Rust bindings offered by BaseSAFE allow you to easily develop new harnesses with a low overhead. So, here you can see our most notable utility functionality, namely the drop-in heap sanitizer. So, sanitizing allocator you can use instead of whatever is actually present in your firmware or whatever you want to fuzz. It has an easy-to-use interface. It should be quite clean. You have extra functionalities or extra functions for freeing and allocating new dynamic memory. We are utilizing already existing Unicorn functionality to build this sanitizing allocator you can easily use in your harness. We are using Unicorn memory hooks mostly to detect various kinds of memory corruption bugs, which are normally hard to find, right? So stack overflows or corruptions like that might directly corrupt your program and lead to a crash, but corruptions on the heap might be only visible at a way later state and not directly when they occur. So we have out-of-bounds accesses. We're placing huge memory hooks over the whole allocated area, and the second we are creating the actual heap. Every time we now want to allocate a chunk, so we call our UCalloc, we decrease the size of this hook to just see if we, with further allocations or uses and memory accesses, run into this hook when we actually try to access memory we haven't allocated before. And we are placing canary hooks. The idea is clear, quite similar to stack canaries. Just before and after every allocated chunk in our heap, we place smaller memory hooks to see if there are immediate corruptions around our allocated chunks. Next up are use after freeze. So every time we are freeing a chunk we don't longer need, we're placing a new kind of hook over this place. And if we're now again accessing this memory chunk, we will notice a use after free and our program will crash. Similar for double freeze, every time we free a chunk, we set its size, which is tracked on our allocator, to 0. And if we try to free a chunk with size 0, we throw a panic. So how would you actually use this drop-in heap sanitizer? You just look in your firmware blob or whatever binary you want to emulate and fuzz where the calls to the actual memory allocator are, and now hook this allocator function. This can be at various levels. For our proof of concept for the MediaTek baseband, we did this at the kernel abstraction layer. And yeah, you just use unicorn hooks, hook the address, and tell the program to instead use the readily available functions of BaseSAFE. So yeah, the BaseSAFE UC free and UC alloc wherever you need it. Make sure you pass the correct return values in the correct return registers and be happy with a fully functioning and sanitized heap. Another topic during our work was how do we actually find out where we want to selectively emulate and fuzz our firmware blob? Of course, there were lots and lots of static analysis. You just have to look at the code, look at what seems interesting, which seems complex enough to fuzz. But we also use something we are calling parser deduction. And actually what we just did is we used coverage to give us a hint on which parser exactly we are looking at the moment. You can see here that when we throw a correct ASIN1 encoded message of, for example, type PCCH into the corresponding correct parser in our firmware, in our baseband firmware, that the coverage was noticeably higher than when we throw just random noise at it or a message of another kind. During our research, we were looking at ARM firmware dump for the Helio X10 processor of the MediaTek family. This baseband OS builds upon Nucleus OS, a real-time operating system, and introduces various layers for different kinds of actions and tasks, obviously. As Dominic mentioned in the beginning, this whole OS is really complex, is dealing with a lot of stuff, with a lot of different kind of messages. We are having inter-process communication using different kind of queues on different levels, like we have queues for IPC on the MediaTek level, but also on the level below, on the Nucleus OS level. And each arriving packet is actually placed in such a queue and then the corresponding parser is called when the packet found its way through the different stages of the Nucleus OS and the MediaTek OS above. We concentrated with BaseSAFE on LTE cellular control plane messages and their parsers, namely for LTE RRC, which is radio resource control, and the EMM, which stands for mobility management. You can see here that while most of our fuzzing we actually did on the RRC handlers, which are very complex ASN1 decoders, we managed to recover a bug in the EMM. And here you can see AFL++ running, how it is fuzzing our harness, our EMM harness, and is now finding the bug. This crash you were just able to witness is a heap out of bounds read and write, and we were able to detect it using our SANitized drop-in heap allocator. The crash occurs in the emergency number list decoder, which is part of tracking area update accept and attach accept messages in the LTE stack. We were actually able to successfully replay this against a real device, namely the one we also dumped the firmware from in the beginning. Here you can see the phone after crashing, how it tries to reboot the baseband processor.
Thank you. So, as a small bonus out of this coverage guided fuzzing, we get actual inputs that are interpreted by the parser in a certain way. So each individual input minimized by AFL will lead to a different coverage path taken inside the parser. So we end up with a large number of valid ASN1 packages or invalid ASN1 packages that the parser parses in a different way. And probably other phones, other parsers parse in a different way too. And so we can reuse these seeds for future runs. In conclusion, with BaseSAFE, we propose a framework that helps in partial rehosting of firmware. So you can take a parser and rehost it into an emulator, where you can use our binary-only sanitization and feedback fuzzing. We implemented a proof concept based on this API and used it to fuzz MediaTek baseband and could even reproduce the crashes found in the emulator on a real device afterwards. The whole project was open sourced and can be used hopefully for future fruitful research. So with this, we want to thank you all for your time and are ready for questions now. Thank you.
Thanks, Dominic and Lucas, for that great talk. As before, if any of you have questions for our speakers from any of our talks, make sure to put those in the session 4 Q&A channel on Mattermost. Next up, we have our final talk of the session, where Wei Chen is going to talk to us about looking at Zigbee security and some things that we could do to make it work better. So take it away, Wei Chen.
Hello everyone, welcome to my presentation. I am Wei Chen Wang, a PhD student at Purdue University Computer Science Department. Today, I will introduce my paper, Analyzing the Attack Landscape of Zigbee-enabled IoT Systems and Reinstating Users' Privacy. It is a joint work with Fabrizio Cicala, Dr. Saeed Rafiul Hussain, Professor Elisa Bertino, and my advisor, Professor Ningui Li. Nowadays, you may or may not notice that our life is bounded with virus of IoT devices. Imagine when you wake up in the morning, you can turn on the light with a voice command. Then the temperature of the air conditioner will be changed, on the thermostat. When you leave home, your door will be locked and the yard alarm will be activated by the smart door lock and alarm. More and more separate devices are connected by the Internet of Things, and more vendors join the IoT world. Among various of IoT protocols, Zigbee is one of the most popular stacks. The Zigbee protocol is lightweight, fast, and can work well with most of the commercial IoT devices, so that many vendors choose Zigbee to develop their own devices. The Zigbee market has increased dramatically in the recent years, and this growth will continue in the following several years. Zigbee is widely used in the market. As a result, it is very easy to become attackers' targets. We have to care the security of the protocol, whether our privacy will be leaked to others, and whether the adversary can attack our devices. Unfortunately, attacks exist, especially during the new device joining process. Let's take a look at how a Zigbee device joins the network. First, from the phone, the user will change the status of the coordinator to the open status. Only in the open status, the new device can join the network. Then, we have a new device preparing to join the network. It will first broadcast this joining request. In the signal level, it is called a beacon request message. Then, the network coordinator will start to identify that device and transfers the network key to the new device encrypted with the trust center link key. Using the network key, the end device can announce itself, and all the other devices in the network will treat it as a part. The network key is used for encryption and decryption of the future communication. We focus on the trust center link key then. It can also called pre-shared link key or the global master key, which stores in every Zigbee devices in the market. However, in 2015, the value of it was exposed to public, and now it is cleared in the specification of the Zigbee protocol. Obviously, any attacker knows the trust center link key as well, so that the network key you received can also be decrypted by the attackers. As a result, the joining process in this way is not very secure. In order to eliminate using the trust center link key, Zigbee aliens developed a new approach to join the network called installation code joining process. Here we are going to see how this installation code joining process usually works. When the Zigbee device comes out, there will be a QR code printed on the shell of the device. We call it installation code. The value of the installation code contains a unique link key which is not known by anyone else. Then the user scans the QR code by the smartphone and sends it to the coordinator through other channels like Wi-Fi or Bluetooth. The joining process starts as the previous approach. The end device broadcasts the beacon request. The coordinator then transfers the network key encrypted with the unique link key. And then the new device joins the network. In such way, the leaked global master key is not used anywhere, so that it provides more security for the devices. However, the feature is not totally secure. Here are two main vulnerabilities. First, the value of the installation code contains the plain text of the unique link key. If the code value is leaked, the whole security cannot be guaranteed. Second, even if the device A joins the network securely in this way, the attacker can still obtain the network key by attacking other devices in the network. Then, attack the device A by using the network key. Meanwhile, this installation code is an optional feature in Zigbee protocol, which most of the outdated devices do not support. It is true that the Zigbee protocol is not 100% secure, but to systematically analyze the security of Zigbee protocol, we make the attack graph of the Zigbee. This graph mainly contains 2 columns and 4 layers. The layer defines the strength of the attackers from low to high. We only care the keys since it is related to decryption of the packets. In the first layer, the attacker has no keys. Then the attacker obtains a trust center link key. Now it is the global master key, which is public, but in the future, the value may change. The third and fourth value is that the attacker obtains a network key and a link key. Those keys are mainly used for commands and the controls. Second, we take a look at the columns. It defines the network status, closed or open. Some attacks are only available for the open status network. Before discussing any attacks, we need to concrete our adversary model and ignore the out-of-scope attack, which is communication disruption. This setting is simple that the attacker does not have any keys. The only thing the attacker can do is to interference the communication within the network. For example, the attacker can launch a denial of service attack. And the denial of service attack does not require any keys and just sending garbage packets to the coordinator in order to block it. It is feasible for any wireless network as long as the attacker is more powerful than the network. We can hardly prevent it, so it belongs to out-of-scope attacks in our paper. Then we take a look at the left bottom corner of the attack graph. Here we come across privacy leakage. We require the attacker holding either the network key or the link key between the victim and the end device. Between the victim and device and the coordinator to decrypt the packets. Here are two parties that can learn the privacy of the device. First, the attackers may know the privacy beginning from the trust center link key, let's say some traces. The attacker can set up a sniffer and listen to the communication between the device and the coordinator. Since the attacker has a trust center link key, the network key can be decrypted. Holding the network key, the attacker can decode all the communication afterwards, such as turn on or turn off the bulb. The second party that may learn the privacy is the malicious device. Because the current Zigbee protocol uses the network key for all the communication, including point-to-point communication. Here is an example. The coordinator is controlling a bulb, but a door lock in the network may also decrypt the messages, which is not common. Then we move back to the attack graph. This time we focus on the right bottom corner. The attack is called user device control, which is more severe than the first one. As long as the attacker has a link key or the network key, no matter the network is closed or open, the attacker can take control of the victim device. This attack is successful because the Zigbee protocol lacks authentication between the coordinator and the end device. Let's take a look at an example. Here, the device tries to join the network, and the coordinator sends the network key encrypted with the trust center link key. After that, the device joins the network successfully. However, here is an attacker hidden nearby and detected the packets transferring the network key. With the trust center link key in hand, the attacker can decrypt all the network key and then impersonate the real coordinator with the same address and send the command to the end device. Since the end device has no way to distinguish between the fake and the real device, as they both have the coordinator's network, and the commands are encrypted with the correct keys, the bot will accept that command, which causes the security concerns. The core problem of the protocol is the leakage of trust center link key, so that attackers can sniff and decrypt the network key. To address those attacks, we propose a new approach. We use the elliptic curve Diffie-Hellman to build a certificateless key exchange approach in order to eliminate the rely on the public known trust center link key. Here is how it works. The end device and the coordinator both have a pair of secret and public value. Then they exchange the public value to the other. When receiving the public value b, the end device can calculate alpha times b and saves the result as a link key. The coordinator receives the public value and calculates beta times a, which is also the link key. The equation of the two link key is guaranteed by the elliptical Diffie-Hellman. Then the network key is encrypted with the link key and sends to the new device. In the future, the link key is used for unicast messages, while the network key is used for only broadcast messages. Here is the detail of the protocol. First, we need to declare that our new approach only modifies the content of existing communication without introducing any new messages. The broadcast request and the broadcast beacon request and the beacons are indicating the joining request. Association request and response contain the identification of two involved devices. We added elliptical Diffie-Hellman public value here. L is the link key calculated by elliptical Diffie-Hellman, and the K is the network key. Any sniffers can capture A and B, but without alpha or beta, the sniffer cannot calculate the link key or decrypt the network key. This approach can address attack 1 and attack 2, since there is no use of trust-center link key, and the network key is only used for the broadcast messages. However, there is a stronger attack called fake device injection, which can work under this situation. This time, instead of attacking the device after it joins the network, the attacker would launch the attack during the joining process. Here, the attacker has a trust-center link key or a valid elliptical Diffie-Hellman key pair, which can be used for joining the network. Here is an example. The attacker cheats both the two end device and the coordinator. Since there is no authentication between the physical device and the device joining the network, the fake end device can inject the network of the coordinator. Moreover, the fake coordinator can connect the real end device. To address these attacks, we use a feature of installation code to help make an authentication. This approach is shown on the right. We can see that the key exchange part is still using the Diffie-Hellman, but we use the installation code as a signature and a verifier to help authenticate. The value of the installation code contains a verifier PK, and at the beginning the user scans it to let the coordinator store it. The end device will sign the whole message and its public value B with the signature SK in order to prove that it is the device being scanned. No fake end device can take part in at this moment, as the signature SK is only known by the end device. Receiving the message, the coordinator would first verify the signature to prevent a fake end device, and then send its public value A concatenating with the hash of A, and the verifier it got from installation code. It is designed to eliminate the potential fake coordinator. The malicious coordinator will not receive the installation code from the user, so that it cannot make the correct hash to pass authentication by the end device. With such approach of key exchange, the fake end device cannot be injected to the network, and the attack 3 is successfully addressed. We implemented our protocols and compared it with the standard and other papers. The software we use is modified from Z3SEC. The hardware we used is USRP and Raspberry Pi. We tested our protocols and evaluated in terms of overhead, security analysis, and convenience. Here is the evaluation result. We have shown that our protocol has low overhead in terms of time, memory, and communication. The extra overhead is almost ignorable compared with the cost of the whole joining process. Our protocol can cover all of the 3 attacks. However, most of the other improved protocol cannot solve attack 3 because they do not provide extra authentication. Finally, our protocol does not require a centralized domain authority. With a centralized domain authority, and the device can store a different pre-shared key. Theoretically, it is helpful. However, in practice, it is hard because Zigbee is a cross-vendor protocol. And a centralized domain authority is very hard to maintain. More details of the experiment setting as well as the evaluation results can be found in the paper. In summary, in this work, we define the attack graph for the Zigbee protocol and address 3 attacks. We propose a new Zigbee joining process using elliptical Diffie-Hellman to exchange the link keys. We propose a more secure Zigbee process by improving the installation code. We evaluate our work and compare it with other improved protocols. Thank you for watching my presentation. I'm happy to take any questions at the end of this section.
Well, thanks, Wei-Chan, for that talk. It's now time to begin our Q&A session. There is still plenty of time for you to add questions to the session 4 Q&A on the Mattermost virtual platform. Let's dive in with some of the questions that we have already received. So we got several questions for the MagicPairing team. The first 2 questions are very similar. Essentially, the question is it possible to actually extract the various keys from these devices? So one person asked about the ACC key and another person actually asked about the link key. Can you actually pull these out, say, from the operating system and use them in some way?
So it depends on what privileges you have, but you have root privileges on macOS, for example. You can extract both the usual link keys and the accessory keys user. And of course, for iOS devices, if you do not jailbreak them, you will never have root privileges. So yeah, it depends. If you get root privileges, you can access all of these keys.
Great. And since we have this team fired up and on the line, we've got a couple more questions for the MagicPairing crew. So the next question was just about functionality. So when if a connection's not set up yet, how do devices communicate? Especially if the link key isn't ready.
Yeah, that depends a bit on what you mean. So before MagicPairing is actually set up, the devices are paired just as any other Bluetooth device using secure simple pairing, and then the accessory key exchange can be done. But if you mean in the moments before MagicPairing is done to be executed, additional traffic except for MagicPairing. So there are a few messages that arrive, and all of these are unencrypted, but there's no meaningful data exchange. And as soon as the link key is ready or derived, then the actual data transmissions start.
Great. So the next question we have for you guys is that we've got a question about your comment or insight that, gosh, it would be nice if other Bluetooth devices could use MagicPairing, not just Apple's. And so, so some of the questions that this idea provoked were, would a third-party implementer have to completely reverse engineer Apple's code? Is anything being made public by Apple directly? And if, say, I wanted to build my own MagicPairing device, how would I tell, say, my iMac that this is a MagicPairing device that you should use instead of, you should use MagicPairing for this as opposed to, say, the normal Bluetooth setup?
Yeah, so currently you would really have to reverse engineer some of the AirPod code. So the accessory key exchange, for example, is done using another proprietary protocol that currently I think only the AirPods speak. So to use MagicPairing, you would have to really pretend to be an AirPod and implement some of these protocols. So the comment was a bit more into the direction that Apple could very easily provide this for other devices. So they could, for example, provide an API where you can do this link key exchange and publicly document this, and then MagicPairing would be very easy to implement. But right now it doesn't really look like they want to make this devices, even for their own devices. It looks like, so yeah, currently it really looks like it's only for the AirPods. And yeah, the second thing was about the broadcast. So yeah, there's in fact actually a Bluetooth advertisement, which is called proximity pairing. And they are used to for Macs and iPads and iPhones to detect that there is a MagicPairing device. When they receive this proximity pairing advertisement, then they will try to start the MagicPairing process to pair to this device that just advertised this.
Great. Well, thank you guys. I think that's all the questions we have for the MagicPairing talk right now. But of course, folks in the audience and attending, if you have more questions, the Mattermost is open. So next up, we had a couple of questions for the BaseSAFE team. So if you guys could log in, I see Dominic and Lucas in my view here. So the first question from Ning Zhang says, great work. And they are curious if your fuzzing effort is currently just focusing on the format parser right now, because, they're also asking if there are functionalities that you want to fuzz that depend on correct emulation of the hardware.
So
that's a challenge.
Of course, emulating the hardware would be a challenge, but basic functionality in the MediaTek baseband is using internal queues and message passing. So you always have a defined entry and defined exit for structs and for data, which makes it, of course, very because we can. Now, if you would have interaction with an external device, you could either fuzz between each interaction of the device, or you would have to start either modeling the device or some false positive may occur.
Dominic, you may want to go to audio only. I'm seeing that your connection isn't doing so great. But if I think that just to summarize what we were able to hear, it sounds like, yes, emulating hardware is a challenge, and that there's a lot of details you'd have to have. Is that about right? And maybe Lucas can chime in if Dominic is still having connection issues.
Is it better now?
It's better right now.
Okay. So yes and no. Of course, it's a challenge, yes, but for specifically the MediaTek baseband, we always had a fixed entry point and a fixed exit, because internally it uses queues for almost every message passing. So this makes it very convenient. In our case, we parse it from a queue and then we put it in the next queue. Of course, then we can exit the fuzzing run. Lucas, do you want to add something?
Yeah, I'm not exactly sure about the scope of the question, but maybe one thing. So there's also a difference between just the baseband image and there's another processor like the DSP. Like if you want to really go into all the hardware stuff, that is in a whole another processor with an own OS. So yeah, we were really fortunate. We basically could stay on the software side of it.
Great. So there's we've got a couple of questions about how you actually extracted the firmware. One person, Stefan, asks, is there additional hardware needed? And Syed Hussein was asking that about the fact that sometimes baseband binaries are encrypted. And if you ran into this problem, and if so, how you handled it.
Yeah, so first of all, the firmware image itself resides on the device. So just present under a system etc firmware, just the image blob there you can use. It has some headers you can strip or you need to strip. And then interestingly, it is only partially encrypted. So only the first few kilobytes are encrypted, the rest of it is plain text. And for this encrypted text, you need the AES key, which fortunately lies just on the device itself again. It's just encoded statically in the kernel. So the moment you have access to the AP, to the usual Android device, you can just, for example, load some kernel module to read out this encryption key, the secret key, dump the firmware blob, decrypt the part which is encrypted, and then you are good to go.
Great. So it sounds like it was a speed bump, less than a major hurdle. Well, great. And of course, folks in the audience and community, you still have opportunities to add more questions, but that's all we have for the BaseSAFE crew right now. The last question in the queue is for Wei Chan and the Zigbee team. And the question from Hanif is, so what's different in the proposed elliptic curve Diffie-Hellman key exchange and the unauthenticated mechanism in WPA3? So, what's the big difference between what you're proposing and WPA3? Because WPA3 apparently uses ECDH for also for generating the pairwise master keys.
Okay. Yeah, thank you, Hanif. It's a good question. And to my mind, ECDH is only a tool and can be used anywhere, and especially for the key exchange. But Zigbee, our proposal using ECDH is for Zigbee only, and we did some modification for that. And we look at ECDH in WPA3, and it seems they use 384-bit key length, which is much larger than ours, because Zigbee device will have much tiny power, and we have to take that into consideration. We cannot use a very big key size so that the device may not compute so fast. So ECDH is very good for the certificateless key exchange, and our proposal is more certificateless, while WPA3 may have certificate somewhere. So we can see like these two, well, our Zigbee protocol and WPA3 both use ECDH. It is a good tool, but ours is for Zigbee specific, and I believe WPA3 is used their own modified ECDH also. Yes, that's it. Thank you.
Great. And we had one more question just come in from Savio. who asks, you discussed some vulnerabilities of the Zigbee joining procedure at the beginning of your talk. Are these applicable to the new Zigbee 3.0 devices, or is it just the older stuff?
Yes, that's a good question. First, when we write this paper, they are mostly about the 2015 version. But yes, of course, Zigbee 3.0 has already come out, and but the specification is not public yet. And most of the devices are still based on the 2015 versions, and they use that specification to build their stacks. But we looked at the Zigbee 3.0 a little bit, like installation code is forced in Zigbee 3.0, and we proposed the vulnerabilities of this joining process. And of course, the Zigbee aliens are now modifying their stacks every day, and they try to avoid these attacks. But to our understanding, if they cannot provide a stronger authentication between user and devices, no matter what kind of authentication secure cryptography works they do, there will still be some vulnerabilities between the device authentication part. Does that answer the questions?
I believe so. And I believe that that is all of our questions. And just looking in the Zoom chat, Savio says, thanks. It did answer their question. So I do have one last question for our first speaker, Zichang. So if you can turn your mic on, I see, okay, I see you're there. My question for your talk was, did you find any interesting case studies or big surprises when you were doing your study of these malicious libraries?
Well, can you hear me?
Yep,
Yeah.
we hear you fine.
Yeah. Yeah, the big surprise, I believe, is the last part. It's about the developer connections with the apps. And we studied the certificates and the signatures of the APKs, which are the Android applications, and the PMLs they're included by them, used by them. And we found that many, about up to 4,000, more than 4,000 corresponding apps are using, are connected with only one or with only 4 PMLs, and they only connected with this signature. So we believe that they may have some, connections between the PMLs and the apps. They may be these PMLs may be developed by the same author, by the same developer, and we believe this may provide new knowledge for finding the developer of the PMLs, because it is really challenged to find the developers of the PMLs directly from themselves.
Yeah, attribution is definitely a hard problem in security broadly. So it's interesting that you guys have a lead on that. I am not seeing any more questions from the audience, so that will conclude our session for this first session of the conference. We'll be back at 10 minutes after the hour for the poster and demo session after a brief break. And so get some coffee and get ready for those posters and demos. Take care.
Hey, welcome back to the 6th section of ACM WiSec 2020. And this section is on firmware, hardware, and crypto. So we have 3 amazing papers lined up in this section, from using firmware to do attack and defense in Wi-Fi environment, to using wireless to attack firmwares, to how to do secure initializations on sensors. Similar to the other sections, the format would be back-to-back presentations, followed by one single period for question and answer. And you can ask your questions in either MetaMost channels or wait till the question and answer period and raise your hand in Zoom. Our first speaker is Matthew. He's a postdoc at NYU Abu Dhabi, and he previously was a PhD student and postdoc at KU Leuven. His interest is network security, software security, and applied cryptography. Today, he will talk about his work on how to use firmware level attackers to do Wi-Fi beacon, to do attack and defense on Wi-Fi beacons. Without further ado, take it away.
Hi, I'm Matti Vanouf, and I'm going to present the paper Protecting Wi-Fi Beacons from Outsider Forgeries. And this is joint work with Prasant Adhikari and Christina Popper. So as the title of the presentation implies, we're going to protect Wi-Fi beacons. Now, before we get into that, what exactly is a Wi-Fi beacon? Well, Wi-Fi networks use Wi-Fi beacons to announce their presence to nearby clients, and they are sent roughly every 100 milliseconds by an access point. And these beacons contain various properties of the network. For example, they contain the name of the network, they contain the supported bit range, for example, whether the network supports the 11N or 11AC standard. And they also contain certain regulatory constraints, for example, the maximum transmission power, and so on. But the problem in practice is that these beacons are not protected and they can be forged by an adversary. And in our work, and in this presentation, we present novel attacks that abuse beacons, and motivated by these novel attacks that we discovered, we implement a defense to prevent outsiders from forging beacons. And we also standardized this defense as part of the 802.11 specification that underpins Wi-Fi. And on top of all of this, we also have an implementation on Linux, and our defense might even become part of WPA 3. But before we get into these details, let's take a step back and look at the history of Wi-Fi security. And here we can see that previously the focus was on protecting transmitted data and not beacons. For example, if we look at web on WPA 1 and 2, they really focus on protecting data only. Now, WPA 3 does mandate that certain management frames are also authenticated. However, unfortunately, this does not include beacons. And even if we look at some very recent additions to Wi-Fi, such as operating channel validation, this only verifies the information about the current channel that the access point is operating on. In other words, even if we use all the modern standards, beacons are not protected and they can be forged by an adversary. And if we look at the contents inside a beacon, we see that there's a lot of information that a beacon contains, and a small amount of information is indirectly verified when you connect to the network. For example, the WPA version that is supported by the network on the current operating channel is securely verified when you are connecting to a network, but all the other information that is contained in a beacon, and here we are only showing a small part of the possible information in a beacon, can be spoofed by an adversary and possibly be abused. So the first thing that we did in our research is that we searched for novel attacks that an adversary can carry out by spoofing these beacon frames. And One of the first attacks that we discovered is what we call a power constraint attack. Namely, as I already hinted at previously, beacons contain the maximum allowed transmit power that a client should be using. For example, if we look at the following beacon content in Wireshark, we can see that it contains the maximum transmit power that is allowed in a certain country. And on top of that, the beacon can even further lower the maximum transmit power below this regulatory maximum. In other words, to simplify, an access point can command the client into using a certain maximum transmit power. And an adversary can abuse this by forging a beacon that instructs clients into using an extremely low transmission power. And in turn, this causes the network connection of the victim to become almost unusable. And that's because the frames that the victim is transmitting will no longer reach the access point. And essentially, this means the client will no longer have a stable internet connection. So if we look in practice, we tested this attack against various operating systems, and we found that an iPad on a MacBook was vulnerable to an attack, and Linux was also vulnerable to attacks. Other devices were not affected. It is unclear why, although we conjecture that after injecting forged beacons, other devices may reset their parameters back to normal once they receive a legitimate beacon. Now, we also found a minor variant of this attack against Linux. Namely, when we were inspecting the source code of the Linux kernel, we noticed that it's also able to parse a vendor-specific information element that belonged to Cisco. And what's interesting about this implementation in Linux is that normally, if we follow the specification, we cannot set a negative maximum transmission power. But by abusing this vendor-specific element of Cisco, we can. And it turns out that if we are able to set a negative transmission limit, then the drivers of Linux do not handle this properly, and as a result, they forcibly are disconnected from the network. So let's show a demonstration of this. In our demo, we can see now that the victim has a stable internet connection. However, as an adversary, we're now going to inject 10 beacons to make sure at least one of them arrives at the victim. And if we now look at the debug messages of the victim, we can see that it indeed lowered its transmission power. And if we look in Wireshark, if we look at the spoofed beacon, it now indeed contains this power constraint element that reduces the transmission power of the client. If the victim now tries to refresh the website or visit a new one, you will see that the website is no longer loading, meaning our attack was successful. Now, a second attack we discovered is that we can lower a victim's bandwidth by spoofing beacons. And this abuses the way that a normal Wi-Fi device transmits frames. In particular, before a Wi-Fi device will transmit a frame, it will first check whether the medium is idle or not. And in case another device is transmitting a frame, it will first wait until this device finished transmitting. And after that, it will wait a very short amount of time called the SIFS interval. And this is mandatory. Every device must wait this amount of time. Additionally, it will wait an amount of time that depends on the priority of the frame that it wants to transmit. This is called the AIFSN period. And for example, if the device wants to send a high priority voice packet, this period is relatively short. While if the device wants to send some background traffic, this period is a bit longer. And then finally, the device will also wait a random amount of time called the backoff window or the contention window. And this is a random value, and it is used to also give other clients an opportunity to transmit as well. But in case during these 3 periods no other device started transmitting, in that case the device can transmit its own frame. Now, what is interesting is that the specific values for these waiting periods are determined by the network configuration. And in particular, they are defined by the beacon. So if we look at a beacon in Wireshark, we can, for example, see that it advertises the specific value for the AIFSN period. Additionally, the minimum and maximum duration of the backup window is also defined in the beacon. And of course, as an adversary, we can spoof beacons where these values are very large. And this means we can force a victim into delaying its transmission for a longer amount of time. And this effectively reduces the bandwidth of a victim. Now, the impact can in fact be much higher than simply lowering the bandwidth of a victim. And that's because if another device starts transmitting during any of these waiting periods, then the device will need to completely restart its waiting procedure. In other words, if there is another nearby client that is actively downloading or uploading a file, our victim may simply never get the chance to transmit the frame, and our attack will result in a denial of service. So we tested this attack in practice, and we found that Linux is affected independent of the network card being used. We also tested some Apple devices, and here we found that the MacBook Pro, the iPhone, and the iPad are all vulnerable. We also tested Windows 10, and here we noticed that the impact depends on the specific network card that this operating system is using. For example, if we use an Alpha or TP-Link USB Wi-Fi dongle, then we found that Windows 10 was vulnerable. However, if we used the built-in network card of certain laptops, which is typically an Intel network card, at least on the devices we tested, then Windows 10 was not vulnerable. Finally, we also tested 2 Android devices, one more recent Nexus 5X device, and it was vulnerable to our attack. But our fairly old Samsung device was not vulnerable to our attack. So let's show a demo of this attack in practice. We will target an iPad device, and we can see that before starting the attack, the iPad has a throughput of about 10 megabit per second. Then as an adversary, we will spoof 2 beacons. And if we look in Wireshark, this spoof beacon has the maximum value for the backup window and also the maximum value for the AIFSN waiting period as well. And if we now measure the throughput on the iPad, we see that it is substantially lower, meaning our attack has succeeded. We also discovered several other attacks. For instance, we discovered a partial machine-in-the-middle attack, and this attack bypasses channel operating validation in Linux. And for the details, I will refer you to the paper. We also discovered battery depletion attacks, where we can spoof beacons to make clients stay awake longer than they normally are. Additionally, we also found that it is possible to send beacons as unicast frames, and this allows us to target specific clients, and this technique worked against all the devices we tested. So how can we prevent these attacks in practice? Well, the idea is to authenticate beacons such that an adversary can no longer spoof them. But before we get into those details, let's first state the goal of our defense. And the goal is to come up with a practical and simple design to encourage adoption in practice. So this means that our cryptographic operations must be efficient and that the bandwidth overhead must be low as well, because beacons are sent at a low bit rate, and even adding a few bytes will consume a significantly higher airtime. Finally, we also want the defense to be straightforward to implement, because then this increases the chance that vendors will actually adopt our defense in practice. And ideally, we will accomplish this by reusing existing cryptographic primitives that were already used in Wi-Fi. So how can we achieve these design goals? Well, we will rely on symmetric encryption, and we will reuse a crypto primitive that is already part of management frame protection. Additionally, we only defend against outsider attacks. In other words, we assume that the adversary does not possess the credentials of the network. And this assumption is similar to how broadcast on multicast traffic is protected in WPA 2.3 as well. So concretely, how does our defense work? Well, we add a new type length value element to beacons. And this element is shown here, and the two most important fields here are highlighted in green. Now, before I discuss the details of these two important fields, I first want to mention that clients that do not recognize this new type length value element, they will automatically ignore it. And this makes our defense backwards compatible with existing Wi-Fi implementations. So first we have the nonce field, and the nonce field is essentially an incremental number that is used to prevent replay attacks. And then the MIC field, which stands for Message Integrity Check, is a CMAC or GMAC authentication tag that is calculated over the beacon. And here the CMAC and GMAC are existing cryptographic primitives of management frame protection. And the interesting thing is that all WPA3 capable devices are already required to support these operations, meaning vendors will already have implemented them by now. So the remaining question now is which key will be used to generate this authentication tag. And here we decided to let the access point generate a new beacon protection key when it starts. And this beacon protection key is always sent to the client when it is connecting. In particular, even if the client may not support beacon protection, the access point will still send this beacon key to the client. And older clients will simply ignore this new key, but new clients will treat it as an indication that the access point supports beacon protection. Now, the interesting thing about this construction is that an adversary cannot manipulate the handshake that transports the beacon key. This means that downgrade attacks are prevented because an adversary cannot somehow remove the beacon key that is being transported to a client. The final important thing to discuss is how that clients handle beacons that are received before they have connected to a network. Because recall that a client only receives the beacon key once it has connected to the network, meaning that beacons that are received before that cannot be authenticated because the client does not possess the key to verify their authenticity. So how can we handle this in practice? Well, our solution is that before a client connects to a network, it will store one beacon as a reference, and it will extract all information of the network from this reference beacon. And when the client now connects to this network, and once it has received the beacon protection key, it can take this reference beacon and then verify its authenticity. And in case this check fails, it means there was an attack, and then the client can disconnect from the network. On the other hand, if the authenticity of the reference beacon can be successfully validated, then the client can send data frames to the network and can operate as normal. Now that we have our defense, an interesting question is how a client should act when it receives a forged beacon. And we decided that in that case, the client should send a notification to the access point. And this allows the access point to detect rogue IPs that are far away. For example, in our illustration here, the rogue IP is out of range of the real IP. However, when a client receives a forged beacon from the rogue IP, it can notify the real access point of this, and then the real access point can take appropriate actions. So now I want to discuss some practical impact of our research. First and for all, we created our specification of our defense in collaboration with Intel, Broadcom, Qualcomm, and Huawei. And our defense is now part of the draft IEEE 802.11 standard, meaning vendors will likely adopt this in practice as well. Moreover, the Wi-Fi Alliance has recently expressed interest in our defense as well, meaning it might become part of an update to WPA3, or it might become part of a separate certification program. Our defense is independently also being implemented by Linux, where the kernel generates and verifies authentication tags, and host AP manages keys and enables beacon protection if it is supported by the network. We will now show a demo of this on a recent Linux kernel, where if we start the access point and view the beacons in Wireshark, we can indeed see that the authentication tag is being added to beacons. If we now connect to this network, the client will indeed receive the beacon protection key, and it will enable beacon protection. As a result, if we now inject the beacon as an adversary, the client will detect this spoofed beacon. In this demo, we made the client print a small debug message, and if we now look at the debug log, we can confirm that the forged beacon has been detected and the attack has been prevented. To conclude our talk, we proposed a defense to prevent outsiders from forging beacons, and our focus on practicality has paid off because our defense is now part of the 802.11 standard. It is independently being implemented by Linux, and it might become part of an update to WPA3. Thank you for your attention.
Thank you for the great presentation. Just a reminder, question and answer would happen at the end of all the presentations, and you're welcome to use the Mattermost channel to ask questions. And our second talk would be presented by Peter, who is a PhD researcher from Hasselt University in Belgium. Hi. So he has been working on 802.11 security and privacy, LoRa privacy, and also side channel analysis and using machine learning techniques. So today he's going to present his work on how to leverage the electromagnetic emission from processors to do novel attacks on reverse engineer the chipsets. All right, without further ado.
Good evening, WiSec. I hope you're all doing great. I'm Peter Robbins from Hasselt University, and today I'm happy to present our study, which was performed in collaboration with Northeastern University, and which is titled Practical Operation Extraction from Electromagnetic Leakage for Sidechannel Analysis and Reverse Engineering. In this study, we'll look at the following problem. Imagine that we have a certain cryptographic device that we want to examine, and suppose that it is also a black box. This means that if we put ourselves in the shoes of an adversary, we can only provide input plaintext, and the cryptographic device will give us the resulting ciphertext. But we don't know which cipher is being used. The adversary can gain a lot of information if they do know the cipher being used, or perhaps even the specific implementation of the cipher. For example, if the cipher is AES, we could perform a SEMA attack, which is a type of sidechannel attack. Specifically for OpenSSL, there might be an old version that contains a different sidechannel vulnerability. Finally, if the cipher is DES, we can brute force the key. However, the adversary can only observe ciphertext, and if the cipher is modern and secure, then this should not give the adversary more information about which cipher is being used. So, the question then becomes, how can we determine the cipher used by a certain device? Well, in practice there are several possibilities. We could read out memory directly, either by hooking up a probe to the flash or random access memory, or by using a debug port on the microcontroller. For example, STM32 microcontrollers can be debugged directly using an ST-Link interface. Another possibility would be to perform a cold boot attack. This attack exploits the fact that some data may linger in memory after a reboot, which means we could upload our own firmware to read it out. In case the device is completely composed of hardware-based implementations, then we could perform hardware reverse engineering, for example, by decapping the chip and then visually determine what the chip is doing using a microscope. Now, each of these methods is quite intrusive and can be mitigated by implementing hardware-based tampering protections. In this study, however, we will be looking at side-channel analysis. More specifically, we will use EM radiation leaking from the device as a basis for determining which cipher is being used. For those of you who are not familiar with side channels are basically just physical properties of hardware that change during computations. Some examples are emitted EM waves, power consumption, timing, acoustic signals, and so on. Side-channel analysis attempts to infer the performed computations by the device by solely observing those physical properties. Some examples are operations of an encryption algorithm, key presses while typing on a keyboard, or even memory read and write instructions. The EM side-channel is what we will focus on in this study. Here, EM signals are inadvertently emitted during computations of the device. And it turns out that properties of this leakage signal, such as the amplitude and frequency, depend on the underlying operation as well as the hardware itself. So the attacker can now send a plain text to encrypt. The device will then inadvertently leak some EM radiation during its computations, and the attacker can then use knowledge of theoretical leakage models to determine which operation or even which key the device used during this computation. One example of such a leakage model is the Hamming distance leakage model, which essentially says that if we have a certain register that is updated to a new value, then its leakage is proportional to the Hamming distance between its old value and its new value. In the figure shown on this slide, you can see an example simulation of leakage for SHA-1 PRF on an x86-64 architecture. Note that we can visually distinguish different parts of its execution, including the SHA-1 and HMAC SHA-1 operations. This is just one example to illustrate the Hamming distance leakage model, but feel free to experiment with our tool to create your own simulations. The tool is freely available on GitHub on this link. As you might have guessed, we will exploit the fact that the EM leakage exhibits certain patterns. More specifically, we will bring the following contributions. We propose a methodology to determine the operation performed by a device given only a singular trace of its EM leakage. Our methodology is based on convolutional neural networks and considers the following 8 operations of interest. Our main target is the ESP8266EX, which features an 80 MHz Tensilica 32-bit RISC processor. From the captured complex value traces, we then consider 2 feature sets. The first is the envelope of the signal, which corresponds to the instantaneous amplitude, and the second is the short time Fourier transform of the signal. All of this is achieved using relatively inexpensive hardware. We used a USRP B210 sampling at 56 million samples per second. Next, we provide a comparison to classical template matching, which is, for example, also used in computer vision to find certain objects in an image. Furthermore, we perform operation extraction, which means that we determine the start and end times of an operation so that it can be extracted from the trace. This is very useful in context of side-channel analysis for creating large datasets of aligned EM traces. Finally, all code of this research is open source, and a 66 GB dataset containing about 70,000 complex value traces is also freely available for download at the provided link. For our practical experiments, we consider 2 possible scenarios, a gray box and a black box scenario. In the gray box scenario, the adversary can trigger operations on demand and has a coarse notion of when operations occur. This makes it easier for the adversary to classify and extract a trace. In the black box scenario, however, the adversary has no control over the inputs. Instead, the operations execute spontaneously and at random. In practice, this scenario could occur when a third-party device sends encrypted and authenticated messages to the ESP8266, which then triggers operations. The ESP8266 device that we will attack is embedded on a NodeMCU Amica development board. This simplifies programming the chip and allows us to upload custom firmware for our experiments. Furthermore, we removed the metal cap from the chip to improve the SNR of the signal and placed a TechBox EM probe connected to an amplifier near the crystal oscillator and the CPU. Now, in order to determine a good tuning frequency for the SDR and position for placing the probe, several approaches are possible. One approach is to execute a simple program and observe the resulting leakage. In this case, the device is alternating between performing XORs of a register with all 1 values and performing NOPs. This will result in a repeating pattern of respectively high and low EM leakage, as can be seen here. Moving on to more complex operations, such as a full tiny AES operation, the next challenge becomes obtaining signals that are usable in our template-based and CNN-based classifiers. As you can see in this figure, the 3 tiny AES signals captured here are quite different and noisy, despite the fact that they contain leakage from the same operation. After performing digital high and low pass filters, we can greatly improve the quality of the leakage signals as shown in this figure. But there is still a lot of noise present. This is problematic for classical template matching, since the templates need to be as clean as possible. To solve this, we capture multiple traces of the same operation and then perform a sample-wise average. The result is a signal that is free of noise, where we can now even distinguish different parts of the execution of AES with the naked eye, such as the 10 encryption rounds shown here. Next, the same procedure can be applied to the other operations in order to build templates for them as well. The figure in this slide shows an example of a template signal for SHA-1 PRF. Note that even though the architecture is different compared to the simulation we saw before, the leakage has a similar structure, with the 4 invocations of HMAC SHA-1 being clearly visible. The second feature set that we consider in our classification approaches is the STFT of the complex signal, shown at the bottom of this figure. Here we have the added advantage that both amplitude and frequency-based features are available, at the cost of some loss in time resolution. Note that similarly to the time domain signal, we can again visually distinguish different parts of the operation taking place in the STFT signal as well. Now that we have templates for each of the operations, it's time to locate them inside unseen traces. One classical approach to achieve this is through template matching, which will be our baseline approach for comparing later experiments. The figure below shows a singular EM trace of tiny AES recorded in a gray box scenario, and our goal is now to classify it. To achieve this, we slide the template signal from earlier over the signal, and for each position we record the correlation and the distance to the template. Then we select either the point of highest correlation or the point of lowest distance, depending on the used metric. For this particular example, tiny AES will have a high correlation at the following position, and the classifier will correctly determine that tiny AES was performed by the device. Evaluating template matching on the entire dataset then results in an accuracy of 36.74%, which is not bad considering that we only used a singular trace for the classification. Note that the classifier seems to overfit on SHA-1 transform. This is because SHA-1 transform is a very short operation, which increases the probability that random segments of noise have a high correlation with this operation. In turn, this results in false positives. The question is now, can we do better? Rather than using only the local features provided by templates, we can try to improve the classification by utilizing CNNs, which have a more global view of the trace to classify. To find a suitable CNN architecture, we based ourselves on the work of Proof et al., where a number of architectures and hyperparameters were compared and evaluated in terms of their effectiveness for sidechannel analysis. We then increase the receptive fields of the convolutional neural network and allow for wider inputs, so that even long operations such as SHA-1 PRF can be detected. Furthermore, we added extra outputs to predict bounding boxes around the traces, along with a corresponding custom loss function to train these outputs. This allows us to simultaneously predict and extract operations from the trace. Finally, we evaluate a 2D variant of the CNN for classifying and extracting operations from STFT-based traces. And the results are shown here. Compared to classical template matching, we already obtain a significant improvement when classifying the test set using the envelope of the traces, because the accuracy becomes 94.43%. Similarly, for the STFT of the traces, the accuracy becomes 94.38%. While these results are indeed very encouraging, keep in mind that we are still operating in a gray box scenario, where the noise preceding and following the operation of interest is very predictable. Later on, we will see how these results compare to the black box scenario. Now, as I indicated before, our CNN can also simultaneously predict the start and end times of an operation. This is useful for the creation of side-channel analysis datasets, since there is no longer a requirement to trigger operations externally, using, for example, a GPIO pin. Instead, the operation can be located directly inside the trace. The downside of this approach is that we need to provide the CNN with manually labeled traces, where the start and end times are determined by a human. But even though the training and test sets both only contain 256 traces, we obtain an accuracy of 34 microseconds on average. For the black box scenario, the situation becomes much more difficult, since we no longer know whether or if an operation occurs. In our experiments, we simulate this by first letting the node MCU perform random calculations that are unrelated to our operations of interest. We call the resulting EM traces noise traces and randomly insert our operation of interest between snippets of these noise traces. As a result, it becomes much harder for the classifier to find and classify the operation. In this case, our best model achieves an accuracy of 55.29%. This brings us to the limitations of this study. For the operation extraction and black box scenario, the start and end times of operations of interest must be manually labeled in order to be precise. In this study, we used 256 traces for training and 256 traces for testing, followed by data augmentation to artificially increase the number of traces in both sets. However, we believe that the accuracy could be further improved by training on a larger labeled dataset. Secondly, we do not consider cross-device templates, which means that the templates created for a Tensilica CPU cannot be used to classify EM traces that originate from an Intel CPU, for example. Finally, we do not account for microarchitectural effects due to pipelining, caching, speculative execution, and so on. As shown in the figure below, these effects can have a significant effect on the EM signature of an operation. Here we have, for example, OpenSSL DES that has been occluded by some caching mechanism, whereas sometimes when this mechanism doesn't occur, the signal looks much clearer. So, what can we learn from these experiments and where can we improve in future works? We've demonstrated a CNN-based classification approach to simultaneously predict and extract 8 operations of interest from singular EM leakage signals. The evaluation of this approach was performed on an ESP8266 device, where the EM traces were captured using a USRP B210. We used 2 feature sets, the envelope and STFT, and then compared the classification results to the classical template matching. Our best results achieve an accuracy of 96.47% in a gray box scenario and with a bounding box error of 34 microseconds. Finally, all data and code has been open sourced on GitHub, and furthermore we have achieved the reproducibility label. In future works, several interesting avenues can be explored further. A first one is bottom-up operation detection for high-end CPUs. Recall that in this study, we focused on detecting high-level operations, such as AES and SHA-1. However, given more sophisticated measuring equipment, it could be possible to fingerprint individual instructions. This would allow us to build a disassembler purely from electromagnetic signals. Although some steps have been taken in this direction, these works consider mostly low-end CPUs. Secondly, accounting for microarchitectural effects poses a significant challenge. Modern CPUs will adapt their execution on the fly based on previous and future variables, which means that fingerprinting of low-level operations becomes increasingly challenging. Third, generalizing towards multiple devices would allow us to build a database of EM signatures that can be applied to multiple devices in order to quickly determine which operations they perform. Perhaps even higher level operations can subsequently be deduced, such as which websites a user visited or which software is installed on a device. And finally, future works could also consider adversaries that have access to more resources, such as hardware with higher sampling rates or setups involving multiple EM probes. So with that, I'd like to end my talk. I hope you all enjoyed, and if you have any more questions regarding this research, I will be available on Zoom during the conference, but you are also welcome to send me an email. So stay safe, and until next time.
Well, thank you for the presentation. I definitely enjoy it. And now, just another reminder, you can ask your questions on Mattermost. I saw a lot of questions coming in already. Thank you. And our last talk of the day is going to be, last talk of the session is going to be by Martin. He is a research associate at Fraunhofer AISEC. He's also a PhD student at Technical University in Munich. He has a background in medical engineering. Now he's venturing into wireless sensor networks and security and user-friendly workflows. Without further ado, I'll let Martin talk about his work.
Hey guys, my name is Martin Striegel. I'm a security researcher at Fraunhofer AISEC Hardware Security Department. And this talk is about firmware distribution for wireless sensor networks. If we want to set up a wireless sensor network, typically we have to do two things. First, we have to distribute firmware to the sensor nodes. And secondly, we have to provision them, which means assigning the sensor nodes to a network and establishing trust between communicating parties. So for example, exchanging keys or certificates. And because we are dealing with large numbers of sensor nodes here, we need a user-friendly and fast way to do it, but also we need a secure way, because obviously we do not want to let the credentials fall in the hands of an attacker. And so far, many approaches have been proposed, but they focus on the provisioning part only, and they assume the firmware to handle this provisioning process is just there. And I'd like to illustrate this with some examples from industry and academia. So typically in the life cycle of a sensor node, there are three parties involved. Firstly, the chip manufacturer, a device manufacturer who joins the chip and wireless connectivity and power supply to build the actual sensor node. And then we have the wireless sensor network operator who wants to deploy and run the sensor network. And many approaches from industry say, okay, let the device manufacturer do it. So this means the device manufacturer supplies bootloader and firmware, creates secret keys or certificates, and adds those to the sensor node. So but this approach has obviously some drawbacks. So firstly, we have to trust the secret generation and probably our firmware, which might be confidential intellectual property, to the device manufacturer. Secondly, we have to be sure that there's a secure channel between device manufacturer and us as operators, from which we can obtain the keys. And lastly, the firmware we want to run on our sensor nodes might not even be available at the time of device manufacturing, which means the first thing we have to do after we get our hands on the sensor nodes is to update their firmware. And this is pretty tedious. Approaches from literature often skip the firmware distribution process and assume the firmware is just there. And they focus on the provisioning part, and typically an out-of-band channel is used to distribute keys and secrets. So those out-of-band channels can be, for example, light or audio, or the operator inserting a secret key into the devices. And this often means that the sensor node has to be supplied with additional hardware interfaces to be able to understand those out-of-band communication protocols. And this makes the sensor node more expensive because, for example, every sensor node needs a display and push button. And we thought, can we do better? And the idea we came up with was an approach we named Box. And we have a literal box. We have a Faraday cage in which we integrate the microcontroller and wireless transceivers. And why do we need a Faraday cage? It provides electromagnetic shielding, which means wireless communications conducted inside sort of stay inside, and an attacker outside has a hard time to understand what's going on inside the Faraday cage. And with this Faraday cage, we can use a user-friendly and portable workflow for distributing firmware and secret keys using over-the-air firmware transmission. And in the next few slides, I'm going to outline how this works. So typically you have three entities, namely the backend, one of our boxes, and the sensor nodes. And the first thing we do is at the backend create firmware images for the sensor nodes and secret keys. And then we ship those to the box, for example, by plugging in the box to the backend. Now in the second step, we place the sensor nodes in the box and shut the box. Every sensor node joins the network the box has created and requests a firmware image. And upon receiving such a request, the box uses one of the secret keys, patches the secret key into the firmware binary image, and then ships the now customized firmware image to the sensor node. And this is done for every sensor node. And the important thing here is that because the box has the electromagnetic shielding, an external attacker cannot eavesdrop on the firmware and key exchange process, and hence not learn the keys. Now in the third and last step, the sensor nodes are being removed from the box and deployed. And because every sensor node shares a secret key with the backend, because the keys have been created at the backend, the sensor nodes can immediately start to transmit their sensor readings and can encrypt and authenticate those data. Now let's see how this process fits into the big picture. As we said before, we want to have the firmware shipped to the sensor nodes as late as possible. And with our approach, we only require that the device manufacturer supplies an OTA-capable bootloader to the sensor nodes. And the important thing here is this bootloader does not need to be customized for a particular sensor node operator. The device manufacturer can just ship a generic OTA-capable bootloader. And using this bootloader, the customization with the sensor network operator firmware is done as late as possible and in-house, which means that we have very long time to develop the firmware, and we do not have to trust our firmware to the device manufacturer. Neither do we have to trust secret keys to the device manufacturer. It all stays in-house at the wireless sensor network operator. So how does the protocol inside the box look like? So remember, the sensor node has a default factory bootloader, and after the sensor network operator places sensor nodes in the box and closes the box, the following protocol takes place. If a sensor node is set up for the very first time, what it's going to do is it requests a customized bootloader from the box. And this customized bootloader includes the public key of the box. And after the sensor node receives and applies this bootloader, it now requests a runtime firmware from the box. Again, upon receiving such a request, the box customizes this firmware with an individual secret key and now signs this firmware with its private key. The sensor node can now validate that this firmware came from a legitimate box and then join the backend network, because the address and credentials for the backend network might also have been included in the firmware image. And afterwards, the sensor node can join the backend network and immediately start to transmit secured sensor readings to the backend. Let's talk about security of this process. We have some assumptions. Firstly, we have to trust the sensor node supply chain, including the bootloader. I think this is a reasonable assumption, because if we do not trust the device manufacturer, well, he could also insert hardware implants. But of course, we would like to have as much as transparency as possible. So for example, doing code reviews and using an open source bootloader for this purpose. We also assume that the sensor network operator is trustworthy and aware of his surroundings. And in a minute, I'm going to talk about why this is important. And lastly, we also assume that the box and the backend are trustworthy and have not been tampered with. Let's talk about eavesdropping. We said we do not want to fall the keys and firmware exchanged to fall in the hands of an attacker. And we achieve this by making sure that the signal strength at the attacker is lower than his receiver sensitivity. And we have two ways of making this sure. Firstly, we transmitted very low transmission power inside the box. For that, we're using a combination of software and hardware attenuators. And inside the box, we have a transmission power so low that the sensor nodes inside the box are barely able to understand the wireless transmissions inside. And in addition, we have the shielding of the box. What can the attacker do to still be able to understand the messages? Well, he can go close to the box to reduce the path loss. And he can also use a big antenna and high gain amplifier. However, as the operator is assumed to be aware of his surroundings, he's going to notice the guy with the big antenna standing right beside him and can take countermeasures. The box also protects against active attacks. So what could an attacker do? He could, for example, jam the wireless channels outside the box. But this is thwarted by the EM shielding because the signal strength inside the box will be much lower than outside of the box. So the attacker has to use massive transmission power to be able to interrupt communication inside the box. The attacker could also try to launch a rogue network outside the box and trick the sensor node in joining that network. And to account for that, the box can employ network monitoring and issue a warning to the operator in case it notices a network with the same network ID and credentials it would use for itself to supply firmware and keys to the sensor node. So the operator is being warned by the box in this case. And lastly, the attacker could try to place a malicious sensor node inside the box. So just build a sniffer node which captures all the transmissions inside the box. And afterwards, the attacker would be able to salvage this sensor node and extract all the overheard secrets and firmware. And to account for that, we can use attestation techniques, which essentially means that the box can interrogate a sensor node and find out whether the sensor node's firmware is a benign or a malicious state. And if it detects a malicious node by that way, it can also warn the operator. Before going to the implementation, I would like to summarize the strength of our approach. So firstly, the sensor node operator can do it all by himself in-house and does not have to provide anything secret to the device manufacturer or any other third party. Additionally, the electromagnetic shielding and the hardware design of the box delivers security. This means that we have the security guarantee if the box is closed during firmware distribution, and the box always meters whether it's closed or open. And if the box is being opened during the firmware exchange, it interrupts this process and issues a warning to the operator. Another thing is what we can do. We have a clear split between setup code, which is placed in the bootloader, and we have the runtime firmware, which then focuses on reading sensors and transmitting those data. And this clear split makes sure that the runtime firmware is not cluttered with functions needed only for setup. And additionally, this contributes to robustness and availability of the sensor node. And lastly, a really cool application is we can use different wireless protocols for different tasks. Picture you have a modern wireless microcontroller which supports multiple transmission protocols. And what we can do, for example, is we can use Wi-Fi for downloading the firmware because it's fast. But in this downloaded firmware image, we can, for example, include a LoRaWAN stack. And now we can use LoRaWAN for transmitting sensor readings to save energy and gain additional range. And such modern microcontrollers in combination with the box allow for really some cool flexible applications. So in this slide, I would like to talk about the implementation of our prototype. To the left, we see an attenuator chain. And as I said before, we do not only rely on shielding alone, we also reduce transmission power to the minimally possible level inside the box. So the sensor nodes can barely hear the signal. With both the shielding and the attenuation, we can lower the signal level at the attacker. And the cool thing is that with this approach, we do not require a jammer mounted outside of the box, which sole purpose would be to lower the signal-to-noise ratio at the attacker. We do not need that here. The user interface is designed to be minimalistic as possible. Essentially, we have two buttons. One is initiates that the box downloads keys and firmware from the backend while being plugged into the backend. The second one starts the firmware deployment process to the sensor nodes. So essentially, the user has to press the button and then close the box, and all the firmware and key exchange takes place inside the box. I mentioned at some points that the box issues a warning to the operator, and this is done using the speakers. So we have an audio interface here. The box at every step provides spoken instructions to the operator. For example, now place the sensor nodes in the box. Now close the box. Or if the operator by accident opens the box during the firmware exchange, it says aborted, box is open, and then the box aborts the process and deletes and invalidates all the keys. So this minimalistic user interface really helps the user in using this box. And to support this claim, we conducted a user study with 31 participants. 20 of those were had a background in computer science and electrical engineering, while 11 had received professional training. So for example, trained mechanics or carpenters. And every subject was tasked to supply 4 sensor nodes using the box. So 4 sensor nodes in one run with the box in parallel. And then using the traditional approach of plugging a cable in the sensor node, connecting it to a backend system, running a script to download the firmware. And we metered how long it took the subjects to do it. We also metered the number of hesitations and errors. And evaluation was done using the standard usability scale, which is a commonly used 10-item Likert scale. And afterwards, we conducted interviews with the subjects. And the results were pretty convincing. So we can see here that using the box takes about 30 seconds for supplying firmware and keys to 4 sensor nodes, while using the wired approach, it took the subjects 24, respectively 22 seconds for the fastest sensor node. So they started at about 45 seconds per sensor node and familiarized with device handling, and afterwards ended up at 24 to 22 seconds. But we see how much the box is faster than using the wired approach. And we also see how well it scales. The more sensor nodes you're able to insert into the box in parallel, essentially the less time you need per sensor node, because the firmware exchange mostly happens in parallel inside the box. We also see that there were less hesitations and errors using the box compared to wired. And this is because sensor node handling is sort of tedious, and many subjects were unfamiliar with that because they had never seen a microcontroller before. And they struggled to insert, for example, the micro USB cable in the sensor nodes correctly. And as every subject did both approaches, in the qualitative feedback from the interviews at the end, they really praised how easy to handle the box is and how intuitive it is. Especially the people without an academic background, like the mechanics, praised how easy it is to use the box and how it transforms otherwise unfamiliar and complex steps in sort of simple mechanical device handling. And the subjects especially liked the spoken feedback, because it reminded them of automatic external defibrillators, which guide the subject through which guide the user through the process. And so in every step they took, they got the audio feedback, and the box told them what they have to do next. And so they felt very, very confident when working with the box. Okay, to sum up my talk, we proposed a user-friendly method for setting up wireless sensor networks, which we call the box. And unlike previous work, we describe a complete workflow for firmware distribution and provisioning. And our box shifts the security-relevant tasks from the operator to the box and reduces the complex task of setting up a wireless sensor network to a few manual steps to be performed. And lastly, this permits even non-tech-savvy operators to set up wireless sensor networks in a quick way and makes them feel confident doing so. And now I would like to thank you for your attention, and I'm looking forward to the discussion.
Thank you for the presentation. Now we're moving into question and answer period. So for the authors responding, could you please make sure that you're here to answer all the questions? So we will do the first presentation first. The first question, this is on the Wi-Fi beacon paper. First question is from Renee. Thanks for the interesting presentation and your focus on practical applicability. This is probably a question of how do clients deal with receiving beacons from APs that don't normally announce their ESSIDs, i.e. hidden SSIDs? I assume they will still be vulnerable, or do you see the difference?
So those devices, well, those networks that use a hidden SSID are indeed still vulnerable. So in our work, there is no difference between a normal network or a hidden SSID. Exactly the same attacks are applicable, and exactly the same defense works as well. Because everything, the network, the access point is identified by the MAC address, and the SSID is, simplifying a bit, it's mainly something that's shown on the user interface.
All right, thank you. So the second question is from Keith. Did you observe any clients recovering from these attacks after receiving true beacons from the real AP after the spoof beacons? Great talk, by the way.
Yes, it's a very good question, and nice to observe it. We indeed observed that. So for example, with the attack where we forced the victim into using a lower bandwidth, we indeed saw that some clients recovered when they received a legitimate beacon. Now, in most cases, we cannot really prevent that. But in the case of the throughput attack, we were able to prevent that because that element contains a flag that indicates whether its values were changed. Basically, all normal beacons don't have that flag because the parameters aren't changed. But as an attacker, we can set the flag, hey, the parameters changed, so only then will the client update its parameters. And this is also discussed in the paper if you want more details. But for other attacks, we cannot prevent that. And that's why we think that some attacks, such as the power constraint attack, it did not work against certain devices. And we weren't able to verify, but my conjecture is that it didn't work exactly because they indeed reset their parameters back to normal.
Thank you. So a follow-up question from myself is perhaps can you analyze the microcode or the kernel code to see if there are differences in handling of those parameters that you're injecting that might give us some hints about why it's more resilient to the attacks?
Yeah, so I guess the first thing that makes certain devices more resilient is whether they process certain elements or not. Because the features that I think we abused in some attacks, I'm not sure if they're always mandatory. So the first part is they may simply not implement it. And then the second part is indeed how they handle the update of the parameters. So if they indeed reset them back, or what's the logic behind that, it can influence how a device is affected.
Thank you. So we have several more questions. There are two that are similar, one for Matthew. Could you explain the differences between your scheme and management frame protection in AO2.11w? And the follow-up question is a little bit relevant, is from Stefan. Wouldn't it be sufficient to move the information such as transmission power or bit rate out of the beacons into the management frames to facilitate the already existing MFP?
So to answer the first question, I would say that the crypto parts are very similar to management frame protection. And in fact, we're reusing parts of their solution. The main addition is that we're now also applying that to beacons. And we provide a mechanism to know when a network supports it, to enable it, and how to handle the case where before connecting to a network, you don't yet know the key. So there are some edge cases where we need to be careful with beacon protection. On the other hand, I would say the core crypto part is actually fairly similar to management frame protection. On the second part, so you could try to move critical fields to other management frames, but then you inevitably end up with the question, okay, which fields are important or not? Then there's the thing, I may not think that this frame is important, but maybe in 5 or 10 years, someone comes up with an attack. So in that case, I think the good approach is to protect everything.
Thank you. Let's see. We have one last question. Have you thought about clients maliciously reporting fake beacons, even if there aren't any? Any thoughts on this?
So that's indeed a very good remark. So in that case, you would have an insider attacker, and we don't explicitly cover that. On the other hand, I think the impact wouldn't be too bad, because our main reason for supporting these rogue networks is so that we can warn the system administrator that, hey, there's something fishy going on with your network. If a client is spoofing these messages, then there's still something fishy going on in a sense. But one way to deal with this, or at least to limit the risk of this, is to only issue a warning when 2 or more devices are reporting beacons. Of course, this can be tricky to control in a home network because you can just spoof different MAC addresses. But maybe in a network such as eDROM, you can uniquely identify users. And in fact, in a network like eDROM, you actually know the real identity of a user. So, if a client tries to pull that off there, you can really say it's this specific user that is trying to mess with me. So it's a valid concern, but I think it can be managed in practice.
Thank you. I think that's all the questions I saw on Mattermost. And I do not see any question on Zoom. So let's move on to the second paper. Thanks, Matthew, for all the answers. Let's move to your paper, Peter. So for the EM leakage paper, the first question is from Florentine. Do you think a similar approach would also work for extracting key materials from these chips?
Yeah, so that's a good question, because we did that actually in a previous work where we used a template attack to synchronize traces from an Arduino device. And then we basically used machine learning to extract the key being used. And honestly, for this project, that was also the initial goal, where we would do this for the ESP8266, which is a much more complex device to attack. And there we targeted the SHA-1 PRF function.
And so what we were able to do was extract the number of bits set to 1 in the first 4 bytes of the key. But there's an issue where leakage from subsequent bytes actually overflow kind of in the leakage of the first 4 bytes. So I'm pretty sure that this is possible. But yeah, the problem was in our case that the SDR simply doesn't have enough samples per second in order to adequately sample the signal. So it would probably require some more advanced hardware to do this for the ESP8266. But it's in theory, it's definitely possible. So yeah.
Thank you. The second question is, does this template matching work on any chipset, or would you have to create the training data for any chip that you want to analyze?
It will always work. But yeah, the higher the clock frequency of the CPU, the more difficult it will be for the attacker to be able to sample the operations. And especially if you have a very short operation like SHA-1 transform, it will be difficult to sample that if you take a modern CPU like you have in your laptop, for example. The ESP8266 has an 80 megahertz CPU, so there it was still possible. But once you start going higher, it becomes harder and harder for the adversary. But again, in theory, it would be possible. And it also depends on the capability of the attacker. If you gather a lot of data from different architectures and then all feed them into a neural network, for example, it could also generalize more. So then the classification could also work for multiple architectures at the same time. But now we just decided to focus solely on the Tensilica CPU for this work.
Great. The last question for you is, how would you design a chip that is resilient to your attack? One way to do it might be to inject a lot of fake operations, but that comes with quite a bit of performance cost.
Yeah. So what you can do indeed is do some fake random operations, and you can definitely make it harder for the attacker in that case. But in practice, the attacker can take multiple measurements. So in this study, we especially considered that the attacker can only take 1 measurement, but in practice, they could take more. So that means that if you take multiple traces from the same operation of interest, and you're doing these fake random operations in between, then yeah, you can still average out these fake operations. So it depends on the capabilities of the attacker again. But the best approach is perhaps to use something like shielding, and that ties into Martin's presentation well, because if you can just shield the electromagnetic radiation from leaving the device, then you can stop the attacks altogether. So yeah.
But shielding only works if the attacker is not like you who take off the shielding, though.
Sorry, could you repeat that, please?
Adding shielding only works if the attacker does not follow your method of removing the shielding. Because many times you have physical access. Yeah.
But even with the shielding applied to the device, we could still measure some leakage. So the shielding was only on the chip itself. And that means that any circuits next to it will still leak some of that electromagnetic radiation. So this was purely done to make the dataset more clean for others to use. But in a practical scenario, if the attacker has a sufficiently strong amplifier, then this would not be a problem, unless the device is completely shielded off, and also perhaps if the chip is designed to minimize EM radiation specifically.
All right, thank you, Peter. I think those are all the questions for your paper. And now let's move on to Martin. So the first question is from Stefan. If I understood correctly, you said the transmission power of the sender inside the box should be as low as possible. Why? To prevent firmware being leaked outside the box?
Exactly, yes. So previous work using Faraday cages for shielding wireless transmissions also required a jammer mounted outside the box. And we had the idea how to get rid of the jammer, and we achieved this by just going very low with the transmission power inside the box. So just by adding software and hardware attenuation. So the key idea is to go as low as possible inside the box. This sort of depends on the sensor nodes used. But typically you can go as low as like minus 90 dBm. So the sensor node still receives the signal, but the outside attacker has a hard time eavesdropping on your signal.
That sounds good. Thank you. The second question is, given the protected beacons are assumed to be sent after clients authenticate with the network, why do we need a new integrity key? Couldn't we just use the same key as AO2.11w?
I think this question
my
is
bad.
targeted at the Wi-Fi beacons.
My bad. Yes, this is for Wi-Fi beacon. Faraday. Okay. Hanif, I will get back to your question after if we have time. For the Faraday cage, why did the experts struggle more with box and wire approve compared to the no voice proof?
we had so much fun during the usability study. What we saw is that the non-experts, for example, using the box, just took the bunch of sensor nodes and threw the whole lot inside the box and closed the box. They didn't care at all about positioning and those things. While the export, some of the experts just took every sensor node and neatly placed it inside the box. And they were so afraid of breaking anything, which took them so much time compared to the non-experts. So I think this, while it was fun to see, it also outlines the point that this approach is suitable for non-tech savvy people, because it just reduces the setup to simple manual actions they're used to and doesn't force them to think, while the experts essentially just thought too much about the whole process. And also the experts afterwards told us, yeah, we would like to have received some more information on what's going on under the hood. While the non-tech savvy people just said, hey, it's cool, I have no idea what's going on, but this device helps me in achieving my goal, and this is all I want.
Thank you. I think we're 2 minutes over. So Hanif, if you don't mind, I'm going to ask you to talk with Matthew offline on the questions. And with that, I'm going to conclude this section. Thank you, everyone, for attending and asking all the great questions. And I will see you 10 minutes after the hour. Bye.
Hello, everyone, and welcome back to WiSec, the final session of today. So today's final session is going to be talking about privacy risks and protections in smart environments. The first talk we have is titled Lost and Found, Stopping Bluetooth Finders from Leaking Private Information. And this is from the CMU lab at TU Darmstadt. And I believe Jiska Klessen is going to be presenting it. So here we go.
Hello, I'm Jiska from the Secure Mobile Networking Lab, and I'm going to present a paper Lost and Found, Stopping Bluetooth Finders from Leaking Private Information. First, I will start with motivation. A Bluetooth item finder is something that you can attach to an item and then no longer lose it. So the idea is, for example, you have your unicorn, you take it to an event, and then you attach this item finder to it, and you have a Bluetooth connection with your smartphone, and then your smartphone is always telling you that your unicorn is in range, and once you lose it, the item finder can make a sound, so you can actually find it again. And then you can also have some assistance. So for example, you could add a GPS location on the smartphone itself. So the smartphone has the GPS, not the item finder. So it's off by a few meters, but you would still have the last known location before you lost the connection to your item. You can also save this last location to a server, so that even if you lose your smartphone, lose your item finder whatsoever, the location would still be on the server and you would be safe to find your unicorn again. And if you bring your unicorn to an event with many other people also having the same app running on their smartphone, what you can do is that, for example, if they take the unicorn somewhere else, they can also run the same app and then synchronize this to the server and have the last location there reported to the server. So this feature is called crowd search. This type of infrastructure is typical for Bluetooth finders, but it can also have multiple security issues. And the first one that we found is that the finder itself does not really have an identity protection, because you have two smartphone apps here, as you can see, and they are both using the same identity to report the last known location to the server, and so it's not really protected. Then most of the apps that we saw had very privacy invasive defaults in their configuration, and also the connection to the server sometimes had issues in the TLS configuration or static API credentials. And the server itself is also a common source for data leakage, because as soon as GPS location is stored somewhere, this location could also obviously leak to anyone else if there is a mistake. The first thing that I did myself within this project is that I analyzed the firmware, because I do a lot of firmware reverse engineering, and if you have a hammer and a nail, in this case IDA Pro, this is the thing that you will always be using. So the finder hardware itself is very simple, as you can see here. It's like the size of just €1 or something, and then you can see all of them are very tiny. But the firmware can either be intercepted from an over-the-air update or the app, or also the hardware itself. The hardware that I looked into, or the firmware actually, is from the NUT tracker, and it has a few basic functions. So it sends an identifier over Bluetooth LE. It accepts connection from a smartphone. It can also play a sound when the connection is lost. And nonetheless, I was like, maybe there is some magic within this firmware, so I loaded it into IDA and analyzed it to just find that, well, it's actually almost the same as the Nordic Semiconductor SDK example, and it's also running on an NRF chip. So there is not really anything to find within it. So yeah, a lot of work, but nothing interesting to be found in there. More interesting are actually the apps that are running the whole logic of connecting to finders, searching for other devices, and so on. And then the question is, if you want to have a lot of finders that you want to analyze, how do you do this? So of course you could buy, let's say, the 100 top sellers, but this would mean buying a lot of different finders, and then maybe still don't have that many different insights. And the first thing is that similar casings often hint to a rebranded product. So there are many finders that have a rounded square form and then some dots in the lower part and then just a different brand name printed onto it. And they are actually all more or less the same. And then some apps also support multiple finders, which also hints that they are technically very similar. And the last part is that you can, of course, even if you don't have a finder yet, download the Android app and then analyze it, for example, for the package names. And then you would know if they might have similar code. And with this method, we excluded a couple of finders in our initial analysis to get very different finders in the end. Here's an app overview of those that we bought. The first one is the NUT finder, then the tile, which are both very common finders. Then there is one which are Mused Gear and iTrack Easy. So this is the squared, rounded square with the dots. Then there's Cube Tracker, which is another very famous tracker. And a bit lesser known is the Gigaset GTAG, which we bought because it just looked different from the other apps. And then there is a large group down here, which you can also buy on Alibaba for just 1 or 2 euros. And it's not just cheap, it's also all of them are based on the same chip. And there are something like 20 different apps that support them, which is a bit strange. So it might be that this is some malware or not, but we don't know it. Maybe there's really just 20 different apps for the same type of finder. So in the next column, what you can see is that they have a declare lost function, at least the first 4 of them, the last 2 don't, which means that you can report your item finder as lost and then have others search for the item. And for this, obviously, they need to report the location to the server. And then there is this strange one, so the keeper, because this one requires a login. So you need a special Gigaset element account. With that you log in. And it's also, so it's required to use the app, but then it's not really used for any crowd search, and also the location, it looks like it's not being sent to the server. So this is a bit weird. Maybe there is still missing functionality. And now the more interesting part is the app security itself. So the first very funny finding here is that there is a TLS connection for the NUT Smart Tracker, but for some reason this is ignored. So there is really code that is hard-coded where they say, yeah, accept any TLS certificate and skip all validation. And this is really weird because this means that TLS doesn't provide any security there. Maybe it was integrated once for testing and never removed or something, but this means that you can break the encryption. And the other apps either just validate the certificate or they do even certificate pinning. Then for the API, there's usually some kind of authentication like a client certificate or AWS credentials. Still, this is something that you can extract from the smartphone app and then use it to authenticate yourself. The firmware location, if there are firmware updates, can be on different places. So first of all, it could be on the server with HTTP. This is the case for the NUT Smart Tracker. And you can actually download all firmware versions, including beta firmwares with this. And then a bit more clever approach is to have it on the Amazon servers and only serve the app for the firmware for the very specific tile version that you have. So this is what tile does. And then you can also store it in the app locally, which is also easy to intercept. Then the firmware encryption, well, there are different variants. Either you don't encrypt it at all, or NUT is encrypting it, but only with a static encryption key. So once you have this, you can also decrypt it. And the best way to solve this is actually how Keeper does it, because they do the decryption of the firmware on the finder itself, which means that you need to open a finder to actually get this encryption key. And if you open a finder and somehow attach like some serial cables and so on and so forth to extract such a key, an attacker who is able to do this can also flash firmware by opening the hardware. So this is out of the attacker model. And then there is some app obfuscation. So the app obfuscation is not very advanced, but at least they stripped some of the function and packet names sometimes. So that makes it a bit harder to analyze, but still not impossible. Now, the very big problem with those Bluetooth item finders is actually the backend. So in the backend analysis, there is all the privacy sensitive data and on the backend, so it's stored there. So if there is some mistake in how the server handles it, there's private data leaking. And there are many sources where it could be. So for example, some of the finders support groups, and then there could be missing group separation or also just no user separation at all. Then there could be protocol failures within the crowd search that somehow within the crowd search and the server interaction leak GPS location and so on. So this is also the most complex part of the implementation because a lot of logic is actually handled by the server. Now you could say, why didn't we use the same super systematic approach as before for the apps? Well, these backends are, all of them are very handcrafted, so they are very special, very different technologies, and also their bugs are all very different. And the next issue is that actually you are on a backend that is used by others, so you need to try to make non-suspicious requests and also some that shouldn't leak data of others. So you would usually buy like 2 trackers and try to get data from the other item owner and so on. So it's all a bit of an issue, testing this carefully and so on. And then what we found for the NUT was very surprising because it has like a half implemented backend for this crowd search. It doesn't work on all apps, but it works a little bit. And then it actually is possible to just request all reports, not just the report of yourself. And this was very surprising because it's also somewhere encoded in the app, but never called like this. So a bit weird. Once again, something that maybe was there for testing. And then we wanted to report this. So we wrote them an email. We sent them like a letter post. We tried to call them by phone and so on. And they never replied. And this was very weird because usually some of the vendors just fix it silently, or at least they reply like they got the email or something, but in this case nothing ever happened. And then we escalated it to CertCC, and they also tried to reach NUT and also couldn't reach NUT. And so this has been open since more than a year by now, and we checked it like every few months if it is finally patched. But because the last time we checked it, it was still open, we redacted all the details of how to obtain the data from the paper. The next thing that we looked into is the tile, and this is also very popular, but they have a bug bounty program, so a very different story here. So it was very easy to report the issues that we found. And what they had as an issue is that the MQTT protocol was leaking data. So MQTT is a status reporting protocol. So you can actually have some responses and so on, and some messages that you can intercept. And in this case, it was possible to see the commands being sent in the backend, including mail addresses, and also the ability to ring a tile if you had the identifier. So we were able, like with 2 tiles, to have the other tile being ringing, even though there was no authorization. And we disclosed this last year, so this is all quite old and nothing that should be exploitable anymore. And for the remaining ones, we found only minor issues, so that indicates that probably there hasn't been any extensive pen testing, but it's not something that was like very severe. And for the Cube tracker, the case was that you could register fake accounts, so you could register an account for an email address without actually verifying the email address, but just verify it on your own. And it was also possible to do some JavaScript prototype pollution. It doesn't look like any code execution on the server, but at least it's causing some internal server error. And they were also using very outdated software. And we reported this to them in January, and they also confirmed the reception. But then there was Chinese New Year and Corona and so on, so it might only be partially fixed by now, I'm not sure. And then the next part of the story is that we said, okay, so the backends are often leaking data that they shouldn't leak, and also the implementations are not that well done. Why not do it on our own? Why not create something that has none of these issues? And this is what we built, so it's called Private Find. And the first part of the protocol is the registration of the finder. For this, we had two variants. So first of all, the setup, which can either be local, or we also have one that is manufacturer verified. And in the local variant, what we do is someone can push and hold a button on the finder, because the assumption is if you have physical access, you could as well steal the item finder. So physical access always means that someone is honest and nearby, because you can also turn it off, take out the battery, and so on. So the owner is pressing the button, and by this starting the registration with the smartphone. And then during this registration, an end-to-end encryption key is generated on the smartphone and sent to the finder. So there is some Bluetooth encryption, but it might, of course, not necessarily be secure, because also Bluetooth has issues. But in this case, we assume it's secure. And then you have this end-to-end encryption key stored on the finder, and then also in the next step stored on the smartphone if the setup worked well. So, and with this, the finder is set up, and in the manufacturer verified variant, we also have the possibility to use a manufacturer key here in addition, to have this part additionally secured if Bluetooth is assumed to be not secure. And then in the reporting part of the protocol, what we do is that the reporters are scanning for finders, and as soon as they find one, what they do is that they message the finder, and now the finder can have like some decisions. So first of all, this "Are you lost?" message is containing a geolocation, and this geolocation is the GPS location of the reporter. And then the finder can decide if it is actually lost. So it can be the case that the finder has not been out of range for too long, just like 1 or 2 minutes. And what happens then is that the finder is not sending back that it is lost. But if it is lost, it uses the end-to-end encryption key, which is only shared with the phone owner, so nobody else can decrypt it. And along with the geolocation, uses it to encrypt the geolocation here from the reporter, and it sends it back with its current randomized ID. And then the reporter is sending this to the server, and then the server can store it there for a while. And now, as soon as the phone owner realizes, oh, I lost my unicorn, it can send a message. And this is a search message here, for example, and it's saying, hey, I have a random ID, and now I found it, and so on, and then also end-to-end encrypted, and then finally the owner is able to find the last location. We also implemented this protocol, and it's publicly available on GitHub in a slightly different variant. And people seem to be using it because they already reported the first bugs on building it and so on. So if you want to try it on your own, just do it and ask questions and so on. And if you have any further questions, our paper is publicly available. You can also ask me on Twitter or write me an email or just open GitHub issues. Thanks for listening.
Wonderful. A reminder that you can use Mattermost to start typing in questions that you might have from that talk, and we'll get to the question and answer session at the end of all three of these talks. Our next talk is entitled "A Purely Edge-Based Visual Privacy Respecting System for Mobile Cameras." It's from a group at Penn State and will be presented by Yuan Yu Shen. All right.
My name is Yuan Yisun. I'm a PhD candidate at Penn State University. Today, I would like to share our work, iRyP, a pretty edge-based, privacy-respecting system for mobile cameras. This is a joint work with Shiqing Chen, Senchun Zhu, and Yu Chen. Mobile devices keep growing every year. It includes the Google Glass, smart tablet, smart watch. People are very interested in sharing their moments on social websites like Facebook, Instagram. Here is a camera privacy example. When people sharing photo online, just like this one, the social website record the time and the location of this photo. Such photo may accidentally capture others' face, like this person. So attacker can easily crawling lots of such photos to tracking this person. Now the attacker know when and where this person show up. This is a big threat. We did some user study. The user study shows that many people do care about this camera privacy issue. The next one is people want to customize their own context-dependable policy rather than a default policy for all scenarios. The third one is camera users like a photographer would like to respecting others' privacy policy as long as doing so would not interfere with the normal use of the media recording. Let's take a look at this scenario. Alice, photographer Alice, take this photo. This person is Bob. Bob has his own policy. His policy is I'm not willing to show up in any photo, but Bob cannot directly talk to each photographer. So our goal is we building a system to help Bob to express his privacy policy to all surrounding photographer. And our system also helps the photographer like Alice to get others' privacy policy to respecting their policy on the photo. Here are some research questions. The first one is how people define their privacy policy. The next one is how to share the privacy policy. The third one is how to match a face in the view. You can see there are lots of faces in the view, how to match the Bob's face. The final one is how to protect the visual privacy, how to protect the Bob's face. The first question is how to define the privacy policy. This is Bob. Bob has his own privacy policy. The policy is photographing is okay, but no sharing. In our system, we encoded the policy in a few bytes. 0 means take photo is okay, but no sharing. 1 means I'm allowed to take photo. You can take photo of me, but you can only share on Facebook, etc. This is how we define the privacy policy in a few bytes. Sorry. The next question is how to share the privacy policy. In our system, we use Bluetooth low energy to broadcast the policy. Bluetooth low energy is a wireless personal short-range network technology. We embed the privacy policy into Bluetooth low energy advertising message, which are periodically broadcast. For each advertising message, there are up to 24 bytes for us to embed our privacy policy without affecting the normal operation of the Bluetooth low energy. Here is some, before we match a face, we first need to detect a face. There are some requirements for a face detection algorithm. It should be high efficiency, high accuracy, and it can also detect the static face and provide the service of the landmark detection. Landmark is just like your eyes, nose, and mouth. You can see the green dot pointing to the eyes and nose and mouth. This is the landmark. In deep learning, we have some algorithm like DP, MV5, ACM, but they all require strong GPU. In mobile or wearable devices, we don't have such GPU. That's why we cannot use such algorithm in mobile or wearable devices. If you use the machine learning, you can use the OpenCV with the hard classifier or cascade, but such algorithms are not very good at detecting static phase, just like this one. I would like to introduce in our system, we use the theta phase. Theta phase is a phase detection algorithm. It meets all our requirements. It's a very high accuracy, high efficiency, and also can detect the static phase and the landmark. Theta phase does not need GPU, and theta phase can detect all angles. Like static phase, you can see with the machine learning, OpenCV, and the hard classifier. When the angle is big, it cannot detect the phase. But the theta phase can detect all phase, even it has a very big angles. For phase matching, we use the perceptual hashing. Bob needs to generate his virtual signature to embed in the Bluetooth low energy advertising message. And based on that, the photographer like Alice can match Bob's face in her photo. We already mentioned that the advertising message, there are up to 24 bytes to store the facial virtual signature. That's far from enough. If you use deep learning, that's far from enough. So in our solution, we use a p-hash. P-hash is one kind of the perceptual hash. We convert one image into a hash value. And given any size of this image, we use V0 resize and the DCT transform. So the result is a 64-bit. And to compare whether two faces is from the same person or not, we use a Hamming distance. Hamming distance is defined by the different base between two hash. The perceptual hash is different from the well-known cryptography hash function, which has what the avalanche effect of a small change in the input. Here we evaluate the sensitivity of facial hashing to the change of the illumination and the facial expression. Here are two examples. In this example, we change the illumination. This one changes the facial expression. As long as we use the appropriate threshold, our system can match these two faces, The perceptual hash is very sensitive to rotation. So when you take photo, we use a landmark to rotate the face back to the T-pose and to the normal. This is T-pose. Another one to reduce the noise is the background. We reduce the background. This is a rectangle face, and we cut a part of it to get the circle one. You can see most of the background is reduced, even not perfect, but most of them are reduced. Bob's face might be captured. This is Bob. Bob's face may be captured in different orientation. Accuracy would be very low if the face orientation of Bob in the photo is much different from that used for the Bob to build his privacy policy. So in our system, we use 3 hash rather than 1 hash to represent Bob's face hash. Bob take photo of his take a front face photo, right face photo, left face photo, and generate 3 hash rather than 1 hash to represent him. When Alice take photo, we use the landmark to calculate. Okay, this is the left face. So left face try to match the left privacy policy data set. So left face match the left face data set. Front face match the front face data set, etc. In this way, we make sure the face match the corresponding data set. The next one is how to protect the privacy. There are lots of ways. Blur is make the face blurred with some famous algorithm, Gaussian blurred algorithm. You can also cartoonize or patch the face, make the face merge with the background. In this paper, we select this algorithm because this one is lightweight than the bottom two. Here is our system architecture, the whole workflow. Bob have a smartphone. They take 3 photos, left, front, and right face. And we first do the face detection to get the face area for each one, and do the face normalization to reduce background, etc. Then we calculate the face hashing, and we have the Bob's policy. Now, finally, Bob's privacy profile have 3 hash: the left face hash, front face hash, right face hash, and his encoded privacy policy. This profile upload to Bob's smartwatch. Bob's smartwatch uses the Bluetooth to keep broadcasting his profile to the surrounding. Now, Alice take photo of Bob. Alice's phone first do the face detection. We detect the face area, and do the face normalization, reduce background, collaborate the angle, then generate the face hash. Then we use the face matching algorithm to match with the Bob's privacy profile. If the match is okay, we do the policy enforcement. The final result is like this one. The face is blurred. We implement the system. The entire system has around the 8,000 line of code, including C and C++ and Java. We use the Android version of Cetaphase and OpenCV2. For Bluetooth low energy operation, we use the classes and API is provided by the Android framework. As we mentioned before, we need to set a threshold for match a face. For this part, threshold of 3 face, including the front, left, and right face, we did an offline analysis with thousands of face and figure that the threshold of Hamming distance 10 or 11 is good for the front face. 8 is good for the side face. More detail can be found at the paper. Take the front face as an example. With this threshold, both the accuracy and the recall are higher than 90%. Here is our overhead evaluation. For one face detection, is use 792 milliseconds. For each additional phase, it needs 3 milliseconds. 300 milliseconds. For phase normalization and phase orientation and calculating p-hash and phase matching, for this part, the processing time is negligible. we did some real-world tests. We tested our system with different scenarios like the classroom, playground, the parking lot, etc. Here is our system interface. After taking photo, our system detects there are 4 persons in this photo, and we get their corresponding policy. Let's take this one as an example. This person is This person is not allowed to others to capture her face. She also not allowed to share her face anywhere. And when a person use our system to share the photo, you can pick a social website icon as this panel. For example, we pick the Instagram, and the final result is this person, the third person and the second person face are blurred. For the others, it's okay. Because in our research, we have a concern with the user, so we just replace their face with the others. There are some security and the privacy analysis. The iRyP won't compromise the base-based user authentication. That means adversary cannot convert the p-hash back to the real image, because that would be a one-way hash function. Another one is the face perceptual hash will not be unique enough to tracking you. We did some experiment when the data site, when lots of people in the data site, there are some collision. I would like to introduce some existing work. The most relevant with our work is EPIC, but the difference is this one require cloud computing. That means in their system, they need to upload the image to upload some data to the cloud and use the GPU to processing image. But in our work, we do not need the cloud. We don't need the GPU. There are some other work, HIDME and privacy tag. Conclusion, we present the iRyP, a purely edge-based, efficient, privacy-respecting system for mobile devices. So we designed some mechanism to improve the accuracy of face matching. We present the Android-based prototype and perform some various offline experiments, and shows that our system has high usability and good accuracy. Thank you.
All right. Again, a reminder to put any questions you have in Mattermost, or we can have them via Zoom discuss-wise after the final talk. And our last talk of the session, last talk of today, it's an exciting one, and I know that because there's an exclamation point in the title. So the final talk is Peekaboo, I See Your Smart Home Activities, Even Encrypted. And this is a collaboration between Florida International University, TU Darmstadt, and University of Padua. And it will be presented by Abagas Akar. All right.
Hello, everybody. My name is Abbas Ajar. I'm a PhD student at Florida International University. And this work has been done with my co-authors from TU Darmstadt and University of Padua. Today, I'm going to be presenting our paper titled Peekaboo, I See Your Smart Home Activities, Even Encrypted. And in this study, what we are trying is inferring user activities from the internal wireless network traffic of smart homes. And what we are showing is actually an attacker can infer the real-time user activities of smart home, even the traffic is encrypted. Here is my outline. First, I'm going to be starting with the adversary model we considered in this paper. Then I'm going to be explaining the experimental setup that we use for the data collection. Then I'm going to be explaining the initial observations that we made. And in these initial observations that we can see that an attacker can infer some information even though the traffic is encrypted. After that, I'm going to be explaining our main contribution of this work, which is multi-stage privacy attack on the smart home users. Then we also propose a defense mechanisms, and I'm going to be concluding the presentation with the related works and conclusions. And in this study, we are considering a nearby passive attacker within the range of wireless network traffic. And this kind of attacker can access to all internal network traffic of smart home. And the attacker wants to inform the ongoing user activities. An example of an adversary with Raspberry Pi equipped with sniffers. And the attacker's aim may be a targeted attack to a high-profile person, or it can be a physical attack like burglary after learning the daily routine of the victim. A defense against this kind of attackers is very challenging because it's very hard to detect the passive attackers, and methods like VPN or Tor doesn't protect against this kind of attack because they do not really hide the internal network traffic. A typical smart home topology, in a typical smart home topology, each IoT devices, they are connected to the hub or they are connected to the router directly. And they're all controlled by a mobile device, and this mobile device is sometimes connected to the router through the Wi-Fi, or they're controlling these devices from a remote location. And in this topology, our target devices are IoT devices. Therefore, we capture the ingoing and outgoing traffic of these devices. And when we look at the traffic from these devices, for example, Wemo Insight Switch, which is using Wi-Fi protocol, we plot the traffic rate, and we can see some peaks at some points. And what we observe that at these points, the network traffic of these devices is changing, and this is resulting in with a huge network traffic exchange between the hub and IoT device. And we can see a similar behavior for Samsung SmartThings outlet, which is actually using a Zigbee protocol. And we can see when the device states change from off to on or from on to off, the device traffic rate is increasing significantly. And also we can see similar behavior for Algoth Smart Lock, which is using BLE protocol. When the device states change from lock to unlock or from unlock to lock, there is a huge increase in the traffic rate. And this kind of similar observations has already been done by other works. However, in this study, our purpose is to be able to propose an attack where the attacker, where we show how the attacker can collect the data to the point where the attacker actually inferring meaningful user activities. And for this purpose, we are proposing a multi-stage privacy attack. And in this multi-stage privacy attack, the attacker first starts with collecting the appropriate the data with the appropriate sniffers, and then the attacker performs device type identification. And after the device type identification, attackers can now separate the traffic generated from different device types. What we mean with the device type is the brand and the type of the device. And in the second stage of the attack, the attacker's purpose is now to decide if a certain activity is performed at that specific time. And after that, attacker can now decide the range of the activities and what time interval the activities are actually performed. And therefore, attacker can use this information and can use this traffic to feed into a classification algorithm. And after that, the attacker can decide which device is performing which activity at that specific time. And using the information from multiple devices, the attacker can now actually perform the user activity inference part of the attack. And here I want to note that even though our attack is working in a cascaded manner, still every stage of this attack leaks partial information about the devices and their actions and can be used by the attacker independently. And in order to evaluate the effectiveness of our multi-stage privacy attack, we installed 22 off-the-shelf IoT devices. And our IoT devices are mainly consist of 3 types of devices. The first type of devices are user-controlled devices, such as smart cameras and smart locks. And the second type of devices are routers, hubs, and gateways. And the third type of devices are smart sensors, such as motion sensor or multi-purpose sensors. And we emulated the user inputs to trigger the white states change, and we performed the analysis offline. And we converted each network traffic into a sequence of packet lengths and times, and each packet is represented as a timestamp, direction, and packet length. Here the direction is referring to if it's an ongoing or ingoing traffic packet. And the packet length information can be directly obtained from the metadata. Therefore, we can also see here that we're only using the information that can be obtained from the metadata of the packet. Therefore, any kind of encryption or any kind of protocol doesn't avoid attacker to obtain from this data. And for the device identifier, in the Wi-Fi protocol, we use MAC addresses. In the Zigbee protocol, we use network addresses. And in BLE protocol, we use advertising addresses. And for the feature extraction, we use the tool called TS-Fresh. And TS-Fresh is automatically extracts 795 time series statistical features from the time series network traffic. And after that, we applied a feature selection algorithm, which decreased the number of features to the 197 features after removing the irrelevant and some missing data. And in the first stage of the attack, the attacker performs the device type identification. And in the literature, actually, there has been many other works that is performing these experiments. Therefore, we only perform this experiment for the Zigbee protocol, which has not been done by other works, and we obtain 93% accuracy with the KNN algorithm. And in this part, I'm going to be showing our results for the device state detection and device state classification algorithms. And for the device state detection, we use 3 features: mean inter-arrival time, mean packet length, and also mean absolute deviation in the packet length. And we used random forest and KNN as a classifier. And for the random forest, we obtained 88% F1 score and 99% accuracy, while we obtained 91% F1 score and 95% accuracy for KNN. And for the device state classification, we performed the actions in the second column. And our results is showing that we obtained 94% F1 score. And in these 2 experiments, we also observed that the worst results are obtained for the sensor-like devices because they are mostly optimized for less communication and because they are relatively constrained devices compared to the user-controlled and hub-like devices. And in the last stage of the attack, the attacker performs user activity inference attack. And for this purpose, we utilize hidden Markov model to model the user activities. And for example, in an example scenario, a user walking from outside of the house to the bathroom. And here we separated this activity into a sequential, 5 sequential sub-activities. For example, in the first subactivity, the user is activating only the device L1, and in the second subactivity, user is activating the devices L1, D1, and L01, and it goes like this. And we can see here that in each subactivity, different set of devices are activated, and using the sequential pattern of subactivities and as well as the set of different devices activated in each subactivity, we can actually predict which kind of user activity is performed at that time. And in order to evaluate our modeling, then we collected data from 10 different users, and we assigned them 6 different user activities. And these user activities are either time-independent or time-dependent activities. A time-independent activity is mostly generating more than one device, activating more than one devices. However, it's mostly consists of one subactivity. On the other hand, the time-dependent activities, they're again activating more than one devices. However, they also consist of more than one subactivities. And we evaluated the results. And when we evaluated the results, we see that we can obtain higher than 90% accuracy and higher than 90% F1 score for every subactivities. And we also observe here that time-dependent activities are mostly less accurate than the time-dependent activities because they mostly consist of more than one subactivities. And in this study, we also propose a defense mechanisms. And here, our defense mechanisms is based on the generation of fake traffic, and we directly injected this fake traffic into the real traffic. And we performed we used this new generated traffic to directly apply into the algorithms that we use, that I defined before, to the device detection and device classification algorithm. And our results is showing that this method is pretty effective because it can actually decrease the attacker success rate to the 26% in the device state detection algorithm, while it can decrease up to the 4% in the device state classification algorithm. And in our implementation, we use this new traffic to apply into the bidirectional traffic. However, it can also be applied into the one-way traffic. It's easier to implement into one-way traffic because it requires the cooperation of either only the IoT device or the cooperation of the hub. However, after a while, the attacker can actually realize that this is a fake traffic because the ingoing and outgoing traffic is not matching. Therefore, it's more effective to apply on the bidirectional traffic. And this kind of defense mechanisms can actually be easily implemented using the open source smart home platforms such as Samsung SmartThings by customizing the apps for each devices. And when we look at the literature, we can see that the identification of network traffic is a well-studied problem. And we can see the examples of web page identification, web user identification, or protocol identification. And recently, some other works also proposed the use of fingerprinting attack on the smartphone, and then we can see the app fingerprinting and location inference attacks. However, applying these traditional techniques in the IoT domain is not straightforward because of the heterogeneous device population of IoT, as well as the attack requires multiple phases in the IoT domain. And when we look at the fingerprinting attacks on the IoT domain, we can see device type identification. We can see some studies performing device type identification, as well as some other studies performing simple device state classification, where they are simply inferring if the device is on or off. Some of these studies also referring to device states inference as the user activity inference. However, in our study, what we are doing is we are proposing an end-to-end attack where we are showing how the attacker can infer the meaningful user activities, starting from how the attacker can collect the data. And in this work, we used 22 devices with Wi-Fi, Zigbee, and BLE, while the previous work mostly worked on a limited number of devices. And first time, I think we used hidden marker model for the user activity inference from the multiple IoT devices. And also in our attack, we turned every stage into a machine learning problem to automate the attack and increase the scalability of the attack from the attacker's viewpoint. And conclusions, we presented a novel multi-stage privacy attack revealing the device types, devices, and ongoing user activities of the smartphone users. And we implemented our attack using 22 off-the-shelf IoT devices with Wi-Fi, Zigbee, and BLE protocol. And our attack worked with very high accuracy. We also presented a mitigation technique based on the spoof traffic generation, and we implemented our defense mechanisms to show its effectiveness. And some future works of our work could be testing the attack that we proposed in this work can be also tested in the wild. Or in this study, we use the same set of devices for the training and testing. However, in a more realistic scenario, the attacker will not be able to have the access to the victim's set of devices. Therefore, a more realistic scenario will be able to training and testing the devices on a different set of devices. And also in this, in our defense mechanisms, what we propose is hiding the device states. However, a more improved defense mechanism could be also hiding the device source and destinations, which could also help to prevent from this kind of attackers. And thank you very much for listening to my presentation. I will be more than happy to answer if you have any questions at the end of the session.
All right, so that concludes the last talk. We have the speakers or any authors who are participating in the Q&A, if they could turn on their videos as well to help with this. And so we have a number of questions already on Mattermost. People can ask questions there. You can also raise your hand in Zoom if you'd like. And if you've asked a question in Mattermost and you'd like to ask it in person as well, we can handle that as well. So we're going to start off with the lost and found paper. We do have a question in there from Alexander Heinrich. I don't know if Alexander wants to ask any of his questions on Zoom, or I can read them.
Well, I can also say it out loud. Yeah, so I thought if you have checked the Bluetooth security of those trackers, or if you focus just on their app security and backend security, and if this new protocol may leak the geolocation of a reporter to such a finder.
So thank you for the questions. So actually, what you can see here on the left-hand side, this is the connection. So between a finder and a Bluetooth device, and this might be a smartphone and the finder. And this is something that you can, of course, attack. But the question is also what you gain by that. So actually, Rapid7 looked also into Bluetooth finders before we did, and they registered multiple CVEs because they were able to change the device name, so write a few get attributes. Now that is not really dangerous in that sense, but of course it's in a firmware and then you can get a CVE, whereas if you have a server, so a handwritten application like running on the server here, and it's leaking customer data, so you wouldn't get a CVE because it's like a custom application. So yeah, we looked a little bit into this, also like if you could write firmware and so on, but yeah, so this one is not really something that I would consider as a severe thing here. I mean, yeah, it depends, of course, on the attacker model. But I mean, if I am nearby a device and flash new firmware, then I could as well like take out the battery or something, or steal the finder. So that's a bit out of scope. So I wouldn't say like that this is a big threat in that sense. Now regarding your second question, so that's basically, so the reporter, that's like the person up here, and they see an item finder, right? And now they report the location to the item finder, and then in our protocol, the finder answers with the encrypted geolocation, and then they can send it to the server. And let's say the item finder itself already knows the location. I mean, if I place it somewhere that's not really something sensitive, like the GPS location is already nearby in that sense. So it's more about metadata maybe leaking about the reporter. But if you are too concerned, something that you could, of course, always do is you could try to not send reports. So you could just be a passive person in that system. So you could use reports of others, but never send reports on your own. And this is also, I think, an option that Mira implemented in the app, so that you just don't send reports.
Yeah, may I add something? So the geolocation of the finder leaks, but not his identity. So you can do the lost finder found report anonymously. So, okay, yeah, the location is leaked, but it's not linked to your identity or to your account or something like that.
Great. I had a kind of different question. This is more of a nuanced, detailed question of your analysis of these devices and their applications. You mentioned in there that Tile wasn't encrypting its firmware, and I'm curious if, while it's not encrypting, is it doing any HMACs or any digital signatures at all? Or just no protection at all?
I'm not particularly sure about that one anymore. But I mean, regarding reverse engineering, it's pretty easy as long as it's not encrypted. Usually you would have some kind of checksum, because if you flash firmware over the air, you could always get corrupted packets and so on. So you need some kind of check in the end.
Yeah, I was just sort of thinking of how you might, try to modify and update and push it onto devices as they may pass you in a busy area. Great. I don't think we have any other questions for the lost and found paper. So let's transition to iRyP. We have a couple questions here for this. Florentine, I believe, has answered his own question, which was looking at potential privacy issues based off that unique value. And in the chat, Senshin responded to that a little bit, but I thought I'd give Ewan an opportunity to also sort of expand on this question. And I'd like to add a little bit to this as well. And while the space maybe collisions in this, in any given area, there may not be, right? So in my area in Raleigh, North Carolina, there might not be any collisions, and that might be enough to track me, and I'm sort of expanding on that.
Yes, we did an experiment. We insert a lot of the user space into the data set. The result is it do have a collision. That means an adversary cannot tracking you with the perceptual hash. Yeah, but in most cases, when you take a photo, only a small people in the view, so there is no collision. Yeah.
So I guess the question I was asking was, what is the likelihood of a collision? Right? Do they happen very, very frequently, or is it no?
No, not frequently. Not frequently. Yeah.
So it still might to some
extent. But when you have a huge data set, for example, 1,000 people in the data set, it do have a collision. Yeah.
Gotcha. Great. Another question from Stefan Klee. I don't know, Stefan, are you available to ask the question yourself, or I can read the question?
Yeah, sure. You can ask a question. Yeah.
So Stefan is asking, how do you handle hash collisions For example, if you're taking, you said they happen in some cases, how do you actually handle the collisions of that? Those sorts of collisions?
Yeah. Our system may accidentally match a person like Bob and both match Bob and Tom. Bob's policy may be allowed sharing, but Tom's policy may be not allowed sharing. So we just pick the stricter one. In this example, it's Tom's policy. Yeah, on it.
And so I had a sort of a related question, I think, that answers this as well. My thought was, could I listen to your hashes and then just go and change your policy? But it sounds like that would just be handled by the same collision policy. Is that correct?
Yeah.
And then Stefan also asks if you think users should have the ability to override what the app may provide. Maybe.
Yeah, maybe. Yeah.
So should you think users should have the ability? If I take a picture of you, okay, should I have the ability to override your policy?
You mean override?
Yeah. Policy. Like if I say, oh, that's what your policy was, but I'm going to share it anyway. Should I have that ability, or should that be?
Yeah, you can customize your policy anytime. You can just push a button and your policy change. All surrounding photographer will get your new policy.
Yeah. I think that the question is more of, should the photographers be allowed to override?
No. We did some experiment. Most photographers would like to respecting others' policy. They would not override.
Great. Do we have any other questions for the iRyP paper? All right, and then let's move on to the last paper, Peekaboo. There are some questions in there, and Alexander, you had some questions, and so you're still on the video, so I'll let you ask.
Yeah, so my question is that the mitigation that was introduced is adding like random traffic there, and how that can maybe influence the congestion of the internet or Wi-Fi network.
Can you hear me clearly? Thank you for the questions. And the mitigation is only a small part of this work, and that will absolutely require more analysis, because we just implemented on the traffic that we collected for the attack purposes. So we haven't implemented the real mitigation like by customizing the apps. Therefore, I guess it will decrease the efficiency of the traffic between the hub and IoT. So there is kind of a trade-off between the security and efficiency at that point.
All right, and we have a question from Hanif Rabari. Hanif, do you want to ask your question, or I can read it?
Yeah, I can ask myself. So let me ask my second question first, which is the follow-up to the previous question. So just to check, and you did not actually evaluate the amount of overhead that your defense mechanism adds to the communication. So I guess that,
yeah, you are correct. We haven't implemented the defense mechanisms. We just used the data that we collected for the attack and simulated the defense mechanisms effectiveness.
I recall a paper published maybe 2014. It was maybe SNP conference that with a similar title saying that the packet injection could have a high overhead, very high overhead actually. So moving on to my other question. So you mentioned that in the identification phase, you identify the devices based on their addresses. And for the Wi-Fi devices based on their MAC address, and for the BLE devices based on their advertisement address. At the same time, these two technologies are actually using some sort of address randomization to prevent such attacks. I wonder, have you considered these defense mechanisms and their impact on the performance of your attack?
So the identification of the device type is the first stage of our attack. So the attacker absolutely needs to identify the device to go further. And However, as you said, some devices, like there are mechanisms that can avoid the attacker to track the device identifier. But among the 22 IoT devices that we use, we haven't seen any devices that are actually deploying these mechanisms. And also I'm aware of that, for example, for Wi-Fi, you might run address randomization. Like in one study, I can send you later if you wish. And the proposed mechanism doesn't actually avoid attacker to track the MAC addresses. And for example, for BLE, normally they're supposed to change their network addresses over time. However, we observed that none of them actually changed their advertising address, not network address, advertising address over time. And so what I mean is we evaluated the practicality of our devices, but you're right, this could avoid attacker to go further in the attack stage. So,
thanks.
I think that's the.
Okay.
Do you have another question? No.
If time permits. If not, that's fine.
No, you can have another question if you'd like.
Oh, okay. So the third question I have posted on there is like, you know, there are some schemes that propose to encrypt the full frame. So the purpose of those encryption is to basically prevent this metadata from being disclosed, like the traffic rate or data rate or packet length and so on. I wonder, have you considered these defense mechanisms?
No, we haven't considered these defense mechanisms in our paper, but the root cause of our attack is the nature of like limited number of activities on the IoT devices. So I'm not sure like if they can avoid this kind of attack, but we haven't tested or we haven't considered in this work.
Okay, thank you very much.
You're welcome.
All right, so let's have a virtual round of applause for all of our speakers. And I'm going to hand things over to Renee and Mikhail, who are going to close us out for today.
Thanks, Will. With this, we would like to close this day. But before, one gentle reminder, the voting for the Best Poster and Demo Award is still up, still ongoing. So if you didn't cast your vote, please do that. If you missed the videos are now on YouTube, so you can still watch them to then cast your vote. And also for the best teaser, there is also the voting still ongoing.
With that, we thank all of you, all participants, both in the meetings on the Mattermost virtual conference venue and of course everybody on YouTube for your participation, and see you tomorrow. Have a good evening, have a good afternoon, have a good night.